Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes its time. Tonight we'll drift gently into one of the universe's quietest yet most mesmerizing performances. The slow, endless turning of planets, each world spinning, tilting, leaning and wobbling through space as if caught in a cosmic lullaby that never truly ends. Have you ever looked up at the night sky and wondered why every planet moves so differently? Why some worlds roll sideways, why some seem to spin backward, and why Earth, of all places, leans just enough to give us spring rain and autumn light? It's a strange thing, isn't it, to realize that motion, something we rarely feel beneath our feet, is shaping every moment of our lives. Right now, wherever you are, your planet is rotating at roughly 1,000 miles per hour, and yet everything feels perfectly still. The teacup doesn't slide from the table, the lamp doesn't drift toward the wall, and somehow this constant spin is the reason for morning, for evening, for the gentle rhythm of waking and resting that has guided life for billions of years. Before we settle into the heart of this journey, I'd love to know something simple. Where are you listening from tonight? Maybe you're in a quiet apartment, lights dim, phone glowing softly beside you. Maybe you're somewhere rural, where the stars are bright enough to remind you that you're sitting on a spinning world, and if you happen to be listening under those stars, perhaps you felt it before. That quiet awareness that Earth is moving, that you're part of a grand rotation you can't see. It's humbling, isn't it? To know that we live our entire lives on something spinning through space, tilted just enough to keep things interesting. If you find this kind of gentle science comforting, soothing, or maybe even a nice way to unwind at the end of the day, I'd be so grateful if you gave the video a like or subscribed. It helps this sleepy little corner of the internet reach others who might need a calm moment too. And now, if you're ready, let's drift a little deeper, because what seems like a simple question, why planets spin and tilt so differently, turns out to be a story written in collisions, chaos, gravity, and time itself. When we imagine the planets of our solar system, it's easy to picture them like dancers in perfect choreography, each one tracing its path around the sun, evenly spaced, orderly, almost polite. But if you could watch their spins, not their orbits, the picture would change completely. Some turn quickly, completing a day in a few hours. Others take months or even years to rotate once. Some lean slightly, some topple almost sideways, one even spins in reverse. It's as if the same cosmic music reached each of them differently. Yet they were all born from the same cloud of gas and dust, the same early solar nursery, roughly 4.5 billion years ago. So how did identical beginnings lead to such different motions? To understand, you have to go back to a time before there were planets, before there was even a sun. Just a vast cold cloud of hydrogen, helium, and tiny traces of heavier elements drifting through the Milky Way. It might have been light years wide, a thin fog of cosmic leftovers from ancient stars that had long since exploded. And in one small region of that cloud something began to shift. Perhaps a nearby supernova sent a shockwave rippling through, nudging the gas ever so slightly. That nudge was enough to start a collapse. Gravity took over, pulling material inward, slowly, relentlessly. And as that cloud contracted, it began to spin. You've probably seen the same thing in miniature, though you might not have realized it. A figure skater drawing their arms inward, spinning faster and faster. That's conservation of angular momentum, one of nature's quiet, unbreakable rules. When something collapses inward, it speeds up to conserve its spin. That simple principle is the beginning of every planet's rotation. As the collapsing cloud spun faster, most of the material gathered at the center, heating up under the growing pressure until it formed a newborn star, our sun. Around it, the leftover dust and gas flattened into a disk, still spinning, still swirling, the birthplace of planets. Within that disk, tiny grains began to stick together, At first, it was just dust clumping to dust, forming pebbles, then rocks, then mountains of rubble. Each collision added mass, and each bit of mass carried its own motion. The growing planetesimals bumped and merged, sometimes gently, sometimes violently, and every impact changed their spin just a little. Over millions of years, these small variations added up, setting the stage for the wildly different rotations we see today. But while all of this was happening, there was no grand design. No blueprint saying this planet should tilt this way and that one should spin in reverse. It was chaos. Every world was shaped by its own particular history of collisions, its own encounters with passing bodies, its own gravitational tugs from neighbours. The solar system was a crowded place back then. There were likely dozens of protoplanets competing for space, slamming into each other, trading momentum like billiard balls in slow motion. Some were destroyed completely, others absorbed their rivals, and a few, like Earth, emerged scarred but stable. Every impact shifted the axis of rotation, every near miss changed the rate of spin. Over time, that chaos froze into a kind of order, but the scars remained written in the angles of the planet's tilts. If you were to stand far above the solar system and watch it unfold, you'd see a swirling disk of glowing dust slowly resolving into bright round worlds. You'd see Jupiter forming early, growing massive enough to dominate the neighbourhood, its gravity flinging smaller objects toward the outer regions or pulling them into stable orbits. You'd see Mars forming with less material, its mass too small to hold onto a thick atmosphere for long. You'd see Venus caught between balance and catastrophe, spinning the wrong way, its surface baking under a runaway greenhouse effect. And Earth, tilted gently, spinning steadily, finding just the right rhythm for oceans, seasons, and eventually life. The variety isn't random, but neither is it deliberate. It's the memory of billions of collisions preserved in motion. It's strange to think about, but without that spin, a planet couldn't really live the way we understand life. A world that doesn't rotate would have one side locked in endless day and the other in perpetual night. The day side would burn, the night side would freeze, and the narrow twilight between them would be the only place anything could survive. Rotation spreads sunlight evenly, lets air and ocean circulate, moderates extremes. The tilt, on the other hand, gives variety, the slow swing of seasons, the shifting sunlight that makes plants bloom, snow melt, and tides of behaviour change in animals and people alike. We owe our comfortable chaos to that quiet 23.5-degree lean, a relic of some ancient impact that knocked Earth off its upright spin but not too far. If we could rewind time to the earliest days of the solar system, the sight would be anything but peaceful. The young sun blazing with solar winds, flares tearing across the void, rocks the size of continents drifting through the haze, planetary embryos colliding in flashes of molten light, craters forming and reforming, every blow reshaping the future. The reason the planets spin so differently isn't that they were born that way, but that each one has been battered, tilted and sculpted by countless events we'll never see. And yet, from this chaos came rhythm, from collisions came balance, from violent beginnings, a kind of slow, graceful motion that feels eternal when you watch it now. You might imagine that over time these spins would slow down, that the planets would gradually come to rest, worn down by friction or cosmic drag. But in the vacuum of space, there's very little to slow a planet's rotation. Once set spinning, it keeps going, perhaps changing slightly over billions of years as tidal forces pull and twist at it, but never stopping completely. Earth's day, for instance, used to be shorter. 400 million years ago, a full rotation took about 22 hours instead of 24. The moon's gravity, tugging on Earth's oceans, has been gradually stealing a bit of our planet's rotational energy, pushing the moon farther away and lengthening the day by a fraction of a second every century. So while our spin feels steady, it's subtly evolving, still part of a cosmic exchange that began when both worlds were molten and close. And then there's the matter of tilt. that delicate angle between a planet's rotational axis and its orbit around the Sun. Why some worlds lean so much and others barely at all is a story of impact, inertia, and long-term stability. The tilt, or obliquity, determines whether a planet has seasons, and how extreme they are. Earth's moderate tilt gives us the gentle rhythm we know. Mars's tilt wanders over millions of years, sometimes nearly doubling, turning its climate chaotic. Uranus lies on its side entirely, spinning almost like a rolling ball. The cause, scientists suspect, was a colossal collision long ago, perhaps with a planet-sized body that struck hard enough to flip it over. Venus may have suffered something similar, only in slow motion. Its rotation slowed and reversed, leaving it spinning backward so slowly that a day there is longer than its year. Each world carries its own story in the way it turns. Sometimes, when we talk about astronomy, it's easy to get lost in the scale. Billions of years, trillions of kilometers, but this story of spinning and tilting is, at its core, about movement and balance. It's the same principle that governs a child's top, a dancer's twirl, a planet's orbit. When something moves, it tends to keep moving. When it spins, it tends to keep spinning, unless something interrupts it. In the early solar system, interruptions were everywhere. Collisions, gravitational tugs, uneven distributions of mass, and each interruption left its mark. So the next time you see an image of the planets lined up in a neat row, remember that beneath that apparent order lies a deep individuality. Every planet spins its own story. Even now, that individuality is changing slowly, quietly. The sun's gravity, the pull of moons, the drag of internal processes, they all work over unimaginable timescales to alter the orientation of worlds. Earth's axis, for example, wobbles in a slow circle, a motion called precession, completing one full turn roughly every 26,000 years. This means that the North Star, which points almost perfectly along our axis today, won't always hold that position. Thousands of years from now, a different star will take its place. The planet's tilt hasn't vanished, it's just turning ever so slightly, like a slow exhale. It's a reminder that even what feels fixed is quietly in motion. Somewhere far out in the solar system, beyond Neptune's orbit, icy remnants of formation still drift. Comets, frozen debris, the leftovers of that first great swirl, they too spin, tumble, tilt and wobble. Some rotate once every few hours, others take days. Many are irregularly shaped, their spins chaotic, changing whenever sunlight warms one side more than the other. Even at the smallest scales, motion is the language of the cosmos. Nothing is perfectly still. Every object, no matter how remote or ancient, carries the echo of that first collapse, that first spin of the cloud that became the sun and all its planets. When you start to think of it that way, the idea of stillness becomes relative. We talk about standing still, but in truth, we never are. The planet beneath us is turning. The planet itself is orbiting the sun. The sun is orbiting the center of the Milky Way. The Milky Way is drifting through space toward another galaxy. Every scale of existence is in motion. The difference is only in speed, in direction, in perception. Maybe that's why watching the stars has always been so calming. They seem eternal, unmoving, yet they remind us that movement and stillness can exist together. The planets spin and tilt differently, but they share the same cosmic rhythm, a balance between chaos and calm. So tonight, as we drift deeper into this quiet dance of worlds, remember that you are part of that motion. The same physics that set the planets turning keeps you gently spinning through space right now. The same collisions that tilted Mars and toppled Uranus once sculpted the world that gives you air, oceans, and gravity to hold you close. The cosmos doesn't repeat itself, but it rhymes softly in patterns of spin, tilt, and balance. The question of why planets spin and tilt so differently isn't just about astronomy. It's about history written in motion, energy preserved through time, and chance crystallized into rhythm. And somewhere in that rhythm, between the turning of Earth and the tilt of the moon's light, you can almost hear the universe whispering its first law, that nothing stands still for long. If you could somehow step backward through time, long before planets, moons, or even the sun existed, you would find yourself adrift in a vast, silent sea of gas and dust. No light, no warmth, no familiar sense of direction, just darkness and the faint, cold breath of particles waiting for something to begin. That something was motion. In the emptiness between stars, motion is often the first whisper of creation. It doesn't arrive suddenly. It builds almost invisibly as gravity starts to notice itself. A few atoms drift slightly closer, then a few more. Over thousands of years, the pull becomes stronger. What was once a calm cloud starts to fold inward, and once gravity begins to collapse a cloud, it cannot help but make it spin. It's a rule so simple that it almost feels inevitable. When a cloud collapses, it must rotate, not because anything pushes it to, but because angular momentum demands it. Just as an ice skater spins faster when they draw their arms in, a collapsing cloud spins faster as it tightens. This quiet, graceful process is the foundation for everything that will come next. The cosmic waltz begins here, not with noise or light, but with a slow spiral that builds from nothing. That spiral will someday become a star surrounded by a swirling disk of dust. Every planet, moon, and asteroid that will ever exist begins as a small note in that immense rotating structure. The first stars to form in the universe were made from pure hydrogen and helium, born in giant clouds that collapsed under their own gravity. But over billions of years, those stars lived, burned, and exploded, scattering heavier elements into space: carbon, oxygen, silicon, iron, the ingredients of planets and people. By the time our own solar system began to form, roughly 4.6 billion years ago, the universe had been thoroughly mixed with this stellar dust. Somewhere in one of the spiral arms of the Milky Way, a cloud of this enriched gas started to fall in on itself. We call it the solar nebula, the birthplace of everything we know. At first, the collapse was gentle, spread over light years, but gravity has patience, and over time it gathered strength. The nebula's rotation, once barely perceptible, grew faster. It flattened into a disk, wide, thin, and shimmering with tiny grains of dust. At the center of that disk, matter piled up until the pressure ignited nuclear fusion, giving birth to the sun. Around it, the rest of the material continued to orbit, each particle tracing its own path through the thin haze of the protoplanetary disk. If you could stand in that disk, you wouldn't see clear planets yet, only a vast plain of gas and fine dust, glowing faintly from the newborn sun's warmth. The light would be filtered and dim, like standing inside a fog that stretches forever. Everywhere you looked, particles would be moving, colliding, sticking, drifting apart, and colliding again. Every one of those small encounters mattered. Each time a grain met another, it shared a bit of motion, a bit of spin, a bit of history. Slowly, those encounters built the first solid worlds. This process is sometimes called accretion, and it's astonishingly simple but endlessly patient. Tiny grains of silicate, ice, and metal cling together by static electricity, forming clumps the size of sand, then pebbles, then rocks. These rocks crash into each other, merge, break apart, and merge again. In the calm regions of the disk, they grow steadily. In turbulent zones, they smash violently, grinding back into dust. The balance between destruction and creation defines everything. The particles that survive each collision are the seeds of planets. In this swirling nursery, the dance of spin begins at every scale. Each clump, no matter how small, has some rotation, inherited from the larger motion of the disk itself. When two clumps merge, their spins combine. Sometimes they align, speeding each other up. Sometimes they oppose, slowing the result down or even reversing its direction. Billions of these mergers happen over millions of years, each one subtly changing the overall pattern. The result is that no two forming worlds end up spinning in quite the same way. The randomness of collisions guarantees diversity. The Sun, massive and radiant, dominates the disk with its gravity. Close to it, where temperatures are scorching, volatile materials like water and methane cannot condense. Only rock and metal survive the heat, forming the seeds of Mercury, Venus, Earth, and Mars. Farther out, where sunlight weakens, ice can survive, allowing the formation of larger, colder bodies, the gas giants and their moons. But even across this immense distance, the entire disk shares a common direction of rotation. Everything orbits the Sun the same way because everything was born from the same spinning cloud. The differences arise not in the direction of orbit, but in the rate and angle of rotation. Those are the signatures of chaos. As these protoplanets grow, they begin to carve gaps in the disk, clearing paths with their gravity. Some sweep up smaller bodies, others fling them away. The regions between the forming worlds become less crowded, but the collisions that still occur are monumental. When two planetary embryos meet, they don't bounce off. They merge in titanic impacts that melt rock and reshape entire worlds. Each one changes how the survivors spin. Sometimes a glancing blow adds a gentle tilt. Sometimes it flips a planet completely. The young solar system is not a peaceful place. It's a construction zone filled with molten worlds and debris, a choreography of violence and creation happening side by side. One of the most important collisions in this dance may have given Earth its moon. The leading theory suggests that a Mars-sized body, often called Theia, struck the early Earth about 4.5 billion years ago. The impact ejected enormous amounts of molten rock into orbit, which eventually coalesced into the moon. That same impact likely altered Earth's spin and tilt, setting the stage for the seasons and stable climate that would later nurture life. The violence of the event seems unimaginable, but it was also a form of balance, an exchange of motion that left the planet spinning steadily, neither too slow nor too fast, neither upright nor completely toppled. Every world experienced its own version of this story. Venus may have suffered collisions that slowed and reversed its rotation. Uranus may have been struck so hard that it was knocked onto its side. Mars may have been destabilized by smaller impacts that set its tilt wandering through the ages. None of these events were planned. They were the natural consequences of motion in a crowded system. When everything is moving and nothing is anchored, collisions are not mistakes. They're the way order emerges. Even as the major planets finished forming, smaller bodies continued to swirl in the outer regions. The asteroid belt between Mars and Jupiter is a collection of objects that never quite formed a planet, their growth disrupted by Jupiter's immense gravity. In the distant Kuiper belt beyond Neptune, icy remnants still follow elongated paths, some tumbling chaotically, others spinning in steady rhythm. These leftovers are fossils of the solar system's earliest days, still carrying the signatures of that first great waltz. If you could speed up time and watch the formation of the solar system unfold in a few minutes, it would look like a slow-motion storm collapsing inward. You'd see the disk flatten, bright rings forming where planets sweep up material. You'd see flashes of light as worlds collide, merge, and cool. Eventually the chaos would settle into the familiar order we know today, 8 planets, each following its own path, each spinning in its own way. But even after billions of years, that original motion remains. The planets still carry the spin of the nebula that birthed them. It's only the details and the tilts, the speeds, the directions, that tell the story of what each one endured along the way. Spin is more than just movement. It's a record of energy and history. Every turn of a planet holds a memory of the forces that shaped it. When scientists measure a planet's rotation, they're not just studying a number, they're reading its autobiography. A fast spin suggests a past filled with momentum, perhaps a history of frequent collisions. A slow spin may point to tidal breaking, where the pull of a nearby moon or star gradually steals energy. An odd tilt might signal a catastrophic impact or long-term gravitational resonance. In the cosmos, motion is memory. There's another layer to this story, and one that connects the small to the immense. The same principles that make a collapsing cloud spin also govern galaxies. Every spiral galaxy in the sky is a vast version of that same process. Gravity pulling matter inward, angular momentum preserving the spin, creating a flattened, rotating disk. The formation of the solar system was simply a smaller echo of what the universe does on grander scales. From dust grains to galaxies, rotation is the universe's default state. Stillness is the rare exception. And yet, despite this universal preference for motion, every spin eventually faces resistance. Planets close to their stars experience tidal forces that can slow them down or even lock their rotation to their orbit, as happened with Mercury and the Moon. Gas giants, massive as they are, experience internal friction that can redistribute their spin over time. Even the Sun's rotation changes slowly as its magnetic field interacts with solar winds. Nothing in the universe spins forever unchanged. Every motion carries within it the seed of its own evolution. The beauty of this process is that it needs no guiding hand. The diversity of planetary spins and tilts is not a mystery of design, but an outcome of natural law applied over immense time. Angular momentum ensures that everything spins. Collisions ensure that nothing spins perfectly. Gravity ensures that, despite the chaos, everything remains bound together. It's a balance between order and disorder, a kind of cosmic compromise that gives rise to endless variety. Sometimes, when you think about all of this, it's easy to forget how connected we are to it. The same forces that spun the planets are still shaping your world right now. The air currents that circle Earth, the spin that creates night and day, the tilt that brings changing seasons. All of it is a continuation of that first rotation. When you watch a sunrise, you're witnessing the planets spin in action. When you notice shadows lengthen in autumn, you're seeing the result of its tilt. The cosmic waltz didn't end billions of years ago. It's ongoing, and you're moving with it every second of your life. Out in the vast dark, beyond where the last sunlight fades, countless other disks are still forming around young stars. Telescopes can now see them, faint halos of dust glowing in infrared, each one a potential solar system in the making. In those distant clouds, the same slow spiral is unfolding again. The same collisions, the same exchange of momentum, the same delicate dance that began ours. Some of those disks may already be forming planets that spin upright, others that will roll on their sides. The diversity we see here is being written elsewhere at this very moment. Every new star is a reminder that the universe never stops dancing. It's worth pausing to think about how this all begins from something so simple. A cloud turning inward under its own gravity. There's no engine, no external force pushing it to spin, just the quiet insistence of physics, the same laws that make water swirl down a drain or galaxies curl into spirals. It's remarkable how much structure can emerge from such simplicity. A little unevenness in motion, a little imbalance in gravity, and suddenly you have planets, moons, rings, seasons, and life. Even now, the early motions of our solar system are being studied in simulations. Computers model billions of particles to understand how different spins and tilts emerge. These digital experiments often confirm what the laws of motion already imply, that variety is inevitable. Even tiny differences in the starting conditions lead to wildly different outcomes. A small change in the angle of an impact, a slightly different orbit, and a planet's entire future can shift. That's why Earth ended up habitable, while its neighbour Venus became a furnace. Not because of a single event, but because of a chain of small variations that compounded over time. The more we learn about exoplanets, those orbiting other stars, the clearer this picture becomes. Observations show worlds that rotate in unexpected ways, some tidally locked, some spinning backward, some tilted so far they experience decades of daylight followed by decades of night. The cosmic waltz isn't limited to our system. It's the universal choreography of matter, repeated endlessly across the galaxy, each system a new arrangement of familiar steps. As we continue to watch the stars and their planets, we're really watching versions of our own story unfolding elsewhere. Every new system begins the same way, a quiet spin in a cloud of dust. Every system ends with worlds that turn and tilt in their own rhythms. Somewhere out there, another planet might be spinning gently, perhaps with its own seas, its own tilted axis shaping alien seasons. Somewhere, another form of life might be looking at its sky, wondering why its world leans the way it does. The dance goes on, endlessly varied, yet bound by the same simple tune. And as you sit here now, listening quietly, maybe you can imagine that original cloud, vast, cool, and still turning slowly in the dark. Every atom of your body once drifted through that cloud. Every element that makes you, from the iron in your blood to the calcium in your bones, was carried in that same swirling disk. The cosmic waltz isn't just the story of planets. It's the story of everything that has ever existed and everything that ever will. The same rotation that shaped the world shaped you. The same tilt that gave Earth its rhythm gave you night to rest and day to wake. Imagine the young solar system not as the graceful clockwork we see in textbooks, but as a storm without calm, a churning ocean of molten rock, gas and fragments colliding endlessly in the glow of a fierce new sun. It wasn't orderly, not yet. It was loud in its own silent way, each impact echoing through the vacuum, each collision a brief flash of heat that faded into the swirling haze. The early system was not a place of circles, but of chaos, a crowded expanse where gravity and motion were constantly arguing over which direction things should go. This was the universe's workshop for turning disorder into pattern, for carving arcs out of randomness, for teaching planets how to move in harmony. At first, there was no clear shape. The sun sat at the centre, but everything around it was unsettled. The disk of dust and debris was thick with motion, clumps forming and breaking apart, countless fragments sharing energy with every encounter. There was no single path that counted as correct. Some objects drifted inward and were pulled apart by solar heat. Others were flung outward, freezing as they went, and some, the lucky ones, found themselves in orbits that didn't cross too many others. Those stable paths were the first steps towards circles. You can think of this stage as nature's slow experiment in balance. Each fragment that formed, each swirl of dust that began to hold together tested what it meant to remain intact. A world could only keep growing if it avoided destruction long enough to collect more material. That meant finding a region of calm, a kind of gravitational rhythm where collisions added rather than erased. Over time, the disk began to thin. The chaotic swirls gave way to lanes of orbiting matter, each one tracing a near circle around the sun. This was how chaos began to draw its own geometry. Still, inside those growing circles, the collisions never truly stopped. When two planetesimals met, they didn't simply merge. They transferred energy, spinning each other, changing trajectories, sometimes leaving trails of debris that would later become moons or rings. The chaos didn't vanish. It became smaller, more focused, confined within boundaries that gravity slowly tightened. The overall structure was becoming circular, but inside those orbits, the storms of creation still raged. If you could have seen it unfold, you might not have recognized it as the birth of a solar system. There would be flashes of molten light, trails of vaporized rock, long shadows cast across glowing dust. The forming planets were not clean spheres yet. They were misshapen, molten, and scarred. Each carried a history written in its spin. A glancing impact could tip a planet's axis. A head-on collision could slow its rotation or even reverse it. No two histories were identical, and that individuality was preserved in motion long after the surface cooled. It's fascinating to think about what these early rotations meant. Spin is energy, and energy must be conserved. Each planet's rotation speed was set by the sum of every collision and gravitational tug it ever experienced. When one object struck another, the outcome depended not just on size but on direction, angle, and timing. Some planets spun up, others slowed down. Some ended up perfectly aligned, others were left leaning. Over time, the countless directions of motion began to average into smoother paths. The orbits became more circular, the rotations more stable, and the once chaotic cloud began to resemble the ordered family of planets we know today. The transformation from chaos to circles was not sudden. It took tens of millions of years for the system to calm. Even after that, the quiet was only relative. Asteroids still collided, comets still plunged inward, and planets still traded subtle gravitational nudges that slightly adjusted their tilts and speeds. But compared to the fiery beginnings, it was serene. The orbits had found balance. The random had become rhythmic. There's a beauty in how simple physics can give rise to this order. Gravity pulls everything inward, but motion resists. The result is not collapse, but orbit. It's the perfect compromise. The same tension that keeps the moon circling Earth keeps Earth circling the sun. The same principle repeats at every scale, from the rings of Saturn to the paths of galaxies. In the earliest days, when the solar system was nothing but debris, that balance was still forming. Every time an object found an orbit where its forward motion matched the sun's pull, a little bit of chaos disappeared. One more fragment joined the quiet geometry of circles. But even circles aren't perfect. In reality, every orbit is slightly elliptical, every path a little stretched. Perfection doesn't exist in nature. Stability does. A slightly imperfect circle can last for billions of years as long as its forces are balanced. The same goes for spin. A planet can wobble, tilt, or precess, yet remain steady overall. What looks chaotic up close often averages out to harmony when you step back. That's one of the quiet lessons the universe teaches through its motion. That balance doesn't mean stillness, and order doesn't mean sameness. As planets cooled, their spins began to stabilize. The molten surfaces hardened into crusts, the cores settled into layers, and internal friction gradually redistributed their momentum. Some planets rotated rapidly, flattening slightly at the poles due to centrifugal force. Others turned more slowly, allowing heat to escape evenly. Each one carried the memory of its youth, written in rotation, speed, and tilt angle. And around them, smaller bodies began to gather. Moons, formed from debris left over from impacts or captured from passing objects. These moons introduced another layer of motion, tugging gently on their parent planets, exchanging angular momentum through tidal forces. Even now, billions of years later, those exchanges continue quietly, adjusting spins by fractions of seconds over centuries. If you look at the planets today, you can still see traces of that long transition. The outer giants, like Jupiter and Saturn, spin rapidly, completing a day in about 10 hours. Their immense size means that even small differences in initial motion translated into tremendous rotational energy. The inner planets, smaller and rockier, spin more slowly. Their history is shaped by impacts and proximity to the Sun. Venus, for instance, rotates so slowly and in the opposite direction of most other planets, likely because of a massive collision or a complex gravitational interaction with the Sun's tides. Mercury, closest to the Sun, has its rotation locked in resonance, spinning 3 times for every 2 orbits. These outcomes are the fingerprints of the early chaos, preserved as motion that never stopped. This process of finding circles from chaos wasn't unique to our system. Everywhere in the universe, disks of gas and dust around young stars follow the same choreography. Observations from modern telescopes show thousands of these disks in various stages of formation, some thick and turbulent, others already clearing gaps where planets are carving their orbits. Each one tells a version of the same story, the slow smoothing of randomness into rhythm. The physics is universal. The results are endlessly diverse. And yet, even after billions of years, chaos never fully leaves. It only hides beneath the surface. The gravitational dance among planets continues to create small instabilities, tiny fluctuations that shift orbits over eons. Resonances form, where one planet's motion subtly influences another's, causing patterns in timing and distance. These interactions can tilt axes, change orbital shapes, or even fling smaller objects into new paths. The system remains dynamic, alive in its motion, always adjusting but rarely collapsing. The stability we see is not static. It's maintained through continuous invisible negotiation. When scientists model the early solar system, they often find that stability is fragile. Small differences in initial conditions can lead to completely different outcomes. A tiny change in one planet's early orbit might have sent others on entirely new trajectories. In some simulations, Earth ends up tilted more steeply or spinning faster. In others, Mars is ejected completely. The actual configuration we have, with its mixture of fast rotators, slow wobblers, and sideways spinners, is just one of countless possibilities. The fact that it works as well as it does is a quiet marvel. The emergence of circular orbits and steady spins also had profound consequences for the evolution of each world's surface. Stable rotation allowed temperatures to moderate, climates to stabilize, and atmospheres to form. A planet that spins too slowly risks extremes of heat and cold. One that spins too fast suffers fierce winds and storms. A gentle, consistent rotation is one of the ingredients for habitability. Earth found that balance by chance, through collisions and gravitational nudges that could have turned out differently. Our comfortable day length, our mild tilt, our reliable seasons, all are echoes of that chaotic beginning settling into order. The circularization of orbits also helped shape the solar system's long-term calm. In a chaotic early stage, orbits cross and intersect, leading to frequent collisions. But as they become more circular, planets separate into distinct regions where collisions are rare. This division created the structure we recognize today: rocky worlds near the Sun, gas giants farther out, and icy bodies beyond. It's as if the solar system learned how to organize itself, how to turn noise into symmetry. Even within that order, rotation keeps each world unique. Spin affects weather patterns, atmospheric circulation, magnetic fields, and even geological activity. On gas giants, rapid rotation stretches storms into long-banded systems. On rocky worlds, slower rotation shapes climate and wind. Without spin, planets would be static spheres, unchanging under the sun. With it, they become dynamic, layered, and alive with motion. The transition from chaos to circles didn't just make the solar system stable, it made it interesting. There's something deeply human about this pattern. We too start in chaos, random, unformed, full of collisions and chance. And slowly, over time, we find rhythm, structure, and stability. The solar system is a reminder that order doesn't arrive instantly. It's something that emerges naturally when energy settles into balance. The planets didn't need guidance to find their paths. They only needed time. If you were to visualize this moment in cosmic history, it would look like a slow tightening of motion. Early on, everything moves erratically, dust swirling in every direction. Gradually, the motion flattens into a disk, then into smooth rings. Within those rings, planets clear space, establishing territories where they can spin undisturbed. The transformation is subtle but profound. What began as a storm becomes a system. What began as chaos becomes circles. Even today, new systems are undergoing this transition. Astronomers have observed young stars surrounded by disks with visible gaps, hints of growing planets shaping their orbits. These systems show us that what happened here is still happening everywhere. The process repeats endlessly, each time producing new variations of tilt, spin, and balance. The universe seems to favour this dance. Chaotic beginnings leading inevitably towards circular grace. When you think of the solar system now, it's easy to picture calm, planets following their tracks, moons keeping pace, everything predictable. But beneath that calm lies the memory of turbulence. Every orbit, every spin, every tilt carries the residue of a time when nothing was certain. The circles we see today were carved out of chaos by the patient hand of gravity. It's a reminder that even the most stable patterns in the universe were born from disorder. The planets that once collided now coexist. Their orbits hum in near-perfect resonance, their spins steady but never identical. The chaos that birthed them hasn't vanished. It's simply been transformed into rhythm. The universe never stops moving from disorder toward balance, even if that balance is temporary. Somewhere, far beyond the edge of our own system, another cloud is beginning to turn, another set of circles waiting to emerge from another sea of chaos, guided by the same patient laws that brought us here. If the early solar system was a dance of motion, then collisions were its most dramatic steps. They were not rare events, not freak accidents, but the very mechanism by which worlds were shaped. In that vast and restless disk of dust and stone, every fragment, every growing planetesimal, was both a builder and a destroyer. There were no soft boundaries, no polite distances. Every orbit intersected with countless others, every few million years bringing a meeting that could shatter or unite. From the outside, it might have looked like chaos, but this was creation through impact, the sculptor's hand shaping planets not with care, but with energy. It's strange to think that something as violent as a collision could be responsible for something as elegant as a planet's spin or tilt, but that's how nature works on grand scales. A single event can redirect a world's destiny, not through design, but through physics. Each impact transfers momentum, alters rotation, and changes orientation. Every planet carries these scars, not always visible on the surface, but written deep within its motion. The way a planet spins, the angle it leans, even whether it spins backward or sideways. These are the fingerprints of ancient violence. The story of these collisions begins when the solar system was still crowded. Hundreds, perhaps thousands of growing bodies shared overlapping paths around the sun. They ranged in size from pebbles to objects hundreds of kilometers across. When two such bodies met, the result depended entirely on speed and geometry. A gentle meeting could merge them peacefully, combining mass and spin. A faster angled strike could tear both apart, scattering debris that would later fall back together. Sometimes collisions were so immense that they reshaped entire worlds, changing not only their rotation, but their internal structure. Take Earth's early history as an example. The planet we live on wasn't born whole, it was assembled. For tens of millions of years it endured one impact after another, each one melting surface rock, stirring metal and mineral, and adding angular momentum. One collision stands out above all others, the impact that created the Moon. About 4.5 billion years ago, a Mars-sized object, often called Theia, struck the young Earth at an oblique angle. The energy released was beyond comprehension, enough to melt much of both worlds and eject a cloud of molten rock into orbit. That debris gradually coalesced into the Moon, and the remaining Earth settled into a new spin and tilt. That single event defined nearly every rhythmic pattern our planet would ever have. Day length, seasons, tides, and the slow wobble of its axis. Without that collision, Earth might have turned too quickly, or perhaps not tilted at all, leaving a world without the subtle shifting of seasons that shape life today. The Moon that emerged became both companion and stabilizer. Its gravity tugs on Earth's oceans, creating tides that move heat and nutrients around the globe. It also steadies Earth's axis, preventing wild swings that could have made the climate unpredictable. The impact that seemed like destruction was, in reality, the event that made long-term stability possible. This is the paradox of cosmic accidents. From chaos comes equilibrium. Earth's story isn't unique. Venus, nearly its twin in size, followed a different path. Today, Venus rotates in the opposite direction to most other planets, and it does so incredibly slowly. A day on Venus lasts longer than its year. Scientists suspect this peculiar motion is the result of a series of powerful impacts early in its formation. Each collision chipped away at its spin until one final glancing blow may have reversed it entirely. Over time, the Sun's gravitational tides could have exaggerated the effect, locking Venus into its sluggish backward rotation. The result is a planet where the Sun rises in the west and sets in the east, an entire world moving against the current of the rest of the solar system. It's a quiet reminder that the universe rarely repeats itself exactly. Two planets can form side by side from the same material under the same star and yet end up utterly different simply because of a few random encounters long ago. Then there is Uranus, a planet that defies easy explanation. It doesn't just tilt a little, it lies on its side, rolling through space like a spinning barrel. Its axis is tilted by about 98 degrees, meaning that for half its long orbit, one pole points directly at the Sun while the other is plunged into darkness. For decades, scientists have tried to explain this bizarre orientation. The most likely cause is a massive collision, perhaps with a body as large as Earth, during the planet's early history. The strike may have been strong enough to knock the planet onto its side without destroying it completely. Some models suggest that smaller, repeated impacts could have achieved the same result, gradually tipping Uranus over like a top-losing balance. Either way, the outcome is a world so tilted that its seasons are unlike anything else in the solar system. For decades at a time, one hemisphere basks in continuous sunlight, while the other sleeps in unending night. Mars, too, tells a story written in impacts. Its northern hemisphere is much lower and smoother than its southern, a vast basin that covers nearly half the planet. Many scientists believe this feature was carved by a single colossal impact, early in Mars's history. Such a blow would have altered not only the planet's surface but also its tilt, contributing to the dramatic variations in obliquity Mars experiences even now. Over millions of years, the planet's tilt has swung from as little as 15 degrees to as much as 35, changing its climate in cycles that may have influenced when and where liquid water could exist. Mars's gentle red deserts are, in a way, the long echo of ancient violence. Not all impacts were catastrophic. Many were small, even beneficial. They delivered water, carbon, and other volatiles to young worlds. Comets and icy asteroids carried these materials inward from the colder regions of the solar system. Without them, Earth might have remained a dry rock. Each impact, no matter how small, contributed to the planet's inventory of essentials. The same impacts that scarred surfaces also seeded possibility. These countless collisions acted as both sculptors and storytellers. Every planet's final form is the result of these exchanges of motion and matter. The energy of an impact doesn't disappear. It becomes rotation, heat, or tilt. It's stored in the way a planet moves. Some of that energy fades over time, dissipated through tidal friction or internal processes, but the core motion remains. The spin of Earth, the backward rotation of Venus, the sideways roll of Uranus, all are permanent records of their histories. When we observe a planet's motion today, we're looking at the sum of billions of collisions long past. The smaller worlds, too, carry their marks. Mercury, with its slow rotation and near-synchronous orbit around the Sun, may once have spun faster before tidal forces and impacts reshaped its motion. Pluto, far from the Sun, spins on its side much like Uranus, likely tipped by ancient collisions in the Kuiper belt. Even tiny moons and asteroids show irregular spins, some tumbling end over end, never finding a single stable rotation. In the absence of atmosphere or erosion, these small bodies preserve their scars perfectly. Every crater, every ridge, every tilt is a fossil of motion. When we study impacts, we're really studying time. Each one is a frozen instant of energy exchange, a snapshot of the solar system in motion. the craters on the Moon, the basins on Mars, the strange elongated shapes of asteroids. All are pages in that record. Even Earth, with its atmosphere and tectonic recycling, still bears traces of its violent youth hidden deep beneath oceans and continents. Our calm world today is built upon a foundation of collisions that never completely ended. Meteorites still fall, small reminders that the sculptor's hand is never entirely still. The randomness of impacts might make the universe seem unpredictable, but there is a kind of order within it. The laws that govern motion are consistent. Every action produces an equal and opposite reaction. Every exchange of momentum follows rules so precise that, given enough information, one could trace a planet's spin back through its collisions. The outcomes seem chaotic because the initial conditions are impossible to know completely, but the principles themselves are unchanging. This balance between chance and law is what makes the universe so endlessly varied, yet fundamentally comprehensible. Consider what these accidents mean for habitability. If Earth had tilted more sharply, its seasons would be extreme. Scorching summers followed by freezing winters. If it had tilted less, the world might lack meaningful seasonal change, leaving ecosystems stagnant. Our mild 23.5 degree tilt is the result of that long ago impact with Theia, moderated by the Moon's stabilizing influence. Venus, with its lack of moon and its reversed spin, developed a stagnant atmosphere that traps heat. Mars, smaller and more erratic in tilt, lost much of its air and warmth. The conditions that made Earth so balanced were not inevitable. They were statistical luck drawn from the chaos of collisions. It's humbling to realize how fragile that balance is. A single impact in the distant past could have shifted the planet's spin enough to make it unrecognizable. In another timeline, Earth could be a world of permanent storms or a frozen sphere without seasons. The sculptor's hand that shaped it was neither careful nor cruel. It simply followed the physics of motion. From that indifference came the delicate balance that allows you to breathe, see clouds drift, and watch the sun set at a slightly different angle each day. Even today, the solar system bears witness to ongoing collisions. Smaller objects still cross paths, asteroids grazing one another, comets breaking apart under solar tides. On Jupiter, impacts occasionally leave dark scars in the clouds, visible even through amateur telescopes. The Shoemaker-Levy 9 event in 1994 was one such reminder. A chain of comet fragments that struck the gas giant in succession, releasing enormous plumes of energy. Jupiter's immense gravity makes it both a target and a protector, drawing in potential impactors that might otherwise have threatened the inner planets. The dance of collisions continues, only more slowly now, stretched across cosmic time. Beyond our system, we see the same patterns. Around other stars, astronomers detect debris disks filled with colliding fragments. Infrared telescopes capture the heat from dust produced by these impacts. Some systems show signs of catastrophic events, planets merging, moons forming, rings appearing. The process is universal. The sculptor's hand reaches everywhere, carving, tipping, and spinning new worlds into existence. When you step back and think about it, the word accident feels almost out of place. Nothing about these collisions is outside the laws of physics. They are inevitable outcomes of motion and gravity. They are the way the universe builds complexity. From an observer's point of view, they seem random, unpredictable, and often destructive. But within the framework of natural law, they are simply the next step in an ongoing process. The universe doesn't plan, but it does persist. Out of every shattered world, something new emerges. Even now, long after the last major planetary collisions, the effects of those early impacts continue to unfold. The spin rates they establish determine how a planet's atmosphere circulates. The tilts they created decide the rhythms of temperature and climate. The moons they produce control tides, stabilize orbits, and create environments for future exploration. The energy of those ancient accidents is still echoing through every day and night cycle we experience. Every sunrise is powered by momentum transferred billions of years ago in an impact that no one witnessed but whose consequences we live within constantly. It's easy to imagine the early solar system as something distant, but in truth, it's still with us. The planets may no longer collide, but they still interact, still trade small bits of motion through gravitational tugs. Those exchanges cause subtle variations in tilt and orbit that continue to shape climates and patterns over geological time. The system never fully stopped evolving. It only slowed to a humanly comfortable pace. From our perspective, it feels eternal, but on cosmic scales, it's still settling. The sculptor's hand, if you could call it that, was patient but relentless. It didn't work with precision tools, it worked with mass and momentum. It didn't plan outcomes, it allowed them. The solar system we see now, 8 planets, dozens of moons, countless smaller bodies, is simply the version that survived. It's the arrangement that happened to balance just enough to last billions of years. If you could rewind and play the same sequence again with the slightest differences in timing or angle, you'd get a completely new system. Maybe one with 10 planets, maybe one with none stable enough to last. Each universe of collisions tells a different story, all written in the same language of impact. And yet, despite all that randomness, what emerged feels harmonious. The planets, though different, all share a common origin. Their motions complement one another, their tilts and spins balanced enough to coexist. It's a kind of accidental symmetry, born from countless asymmetric events. The sculptor's hand wasn't careful, but it was consistent. It worked slowly, over time, guided only by the quiet logic of physics. So when we look at the planets now, the steady roll of Earth, the retrograde spin of Venus, the sideways tilt of Uranus, we're seeing not isolated curiosities, but the outcomes of a single process repeated billions of times. Every spin is a memory, every tilt is a trace of impact. Every world, no matter how serene it looks today, was once molten, battered and reformed. The serenity we see is simply the calm that follows after the sculptor's work is done, and somewhere out there, in the cold reaches of another forming system, that same sculptor is still at work. Clouds are collapsing, fragments are meeting, collisions are building new planets. Each impact is another touch of motion, another tilt waiting to happen. The universe doesn't stop shaping, it only shifts where it's shaping next. The story of collisions and cosmic accidents isn't just the past, it's the ongoing rhythm of creation, still unfolding quietly across the stars, waiting for new worlds to carry their own scars of motion, new spins, new tilts, and new possibilities. Among all the planets that circle the sun, there is one that seems to move to its own quiet rhythm, a world that looks like a twin to Earth yet behaves like an opposite. Venus, nearly the same size, the same mass, formed from the same ancient cloud, and orbiting in nearly the same region of space. At first glance it should have been another Earth, bright, rocky, wrapped in an atmosphere warmed by sunlight. But everything about it, from the direction of its spin to the heat of its air, tells a different story. It's as if two worlds began side by side, then drifted apart in destiny, one turning gently toward balance, the other sinking into extremes. To understand why planets spin and tilt so differently, Venus is perhaps the most revealing example of how small variations can turn a familiar world into an alien one. Seen from a distance, Venus looks calm. Its pale yellow clouds reflect sunlight so strongly that it shines brighter than any other planet in our sky. To the naked eye, it's beautiful, serene, almost gentle. But beneath that cloud layer lies a different reality. A surface hot enough to melt lead, air so thick it would crush a person in seconds, and winds that sweep the planet's upper atmosphere at hundreds of kilometers per hour. This is a world that hides its violence behind brightness, and the reason for its strange state lies in part in the way it spins. Venus rotates backward compared to almost every other planet. Its day lasts longer than its year, and its tilt, though small, behaves in ways that make its seasons nearly vanish. These simple facts about motion explain almost everything about the planet's present condition. In most planetary systems, the natural outcome of formation is that all the planets spin in roughly the same direction, the same way they orbit their star. This comes from the original spin of the protoplanetary disk. All matter in that disk shared the same general angular momentum, so every world born from it inherited a similar sense of direction. That's why the planets orbit the Sun counterclockwise when viewed from above the solar north. It's why most of them spin the same way, with the Sun rising in the east and setting in the west. Venus, however, does the opposite. The Sun rises in the west and sets in the east. Its rotation is retrograde, moving against the flow. This backward spin raises a simple question. How could a planet end up turning the wrong way? The answer isn't simple at all. There are two main possibilities, and both trace back to the early chaos that shaped every world. The first is that Venus may have suffered one or more enormous collisions that reversed its rotation. A glancing impact with a body of substantial mass could have slowed its spin, tipped it, or even flipped it entirely. Because Venus rotates extremely slowly, just once every 243 Earth days, even a modest shift could have been enough to change its direction. The second possibility involves long-term tidal interactions with the Sun. Over billions of years, solar gravity can subtly distort a planet's rotation, especially if that planet's atmosphere and internal structure dissipate energy unevenly. Gradually, those small tugs can cause the planet to lose rotational speed, and in some cases to reverse direction entirely. Venus may have experienced both, collisions early on and tidal breaking later, combining into the strange, languid rotation we see now. When you think of it, a single day on Venus lasts longer than an entire year there. Venus completes one orbit around the Sun every 225 Earth days, but it takes 243 Earth days to spin once on its axis. This means that if you could stand on its surface, you would experience a sunrise, then months of unbroken daylight, then a sunset, followed by months of night. Yet the planet's thick atmosphere circulates so rapidly that the upper clouds race around the planet in just 4 Earth days, creating a strange paradox. The winds above move faster than the surface itself. The atmosphere behaves like a separate world, independent of the slow, dragging planet beneath it. That slow spin is one of the keys to Venus's extreme climate. Because the planet rotates so gradually, heat builds up unevenly. The thick carbon dioxide atmosphere traps sunlight with immense efficiency, preventing the heat from escaping into space. This runaway greenhouse effect raises surface temperatures to around 465 degrees Celsius, hotter than Mercury, even though Venus is farther from the Sun. The rotation also affects how air circulates, creating vast Hadley cells that extend from the equator to the poles, distributing warmth but maintaining a global uniformity of heat. There are no true seasons on Venus. Its axis is tilted by only about 3 degrees, meaning the sunlight it receives changes very little over the course of its orbit. Instead of seasonal variation, Venus experiences an eternal equilibrium of heat, pressure, and slow, silent rotation. The combination of slow spin and thick atmosphere has another fascinating consequence. It may help explain why Venus's magnetic field is so weak. On Earth, the planet's rapid rotation helps drive the motion of molten metal in its outer core, generating a strong magnetic field that protects us from solar radiation. Venus, turning so slowly, likely lacks the same internal dynamo. Without that magnetic shield, solar wind has been able to strip away lighter elements from its upper atmosphere over time, leaving behind heavier gases like carbon dioxide and sulfuric acid. What remains is a suffocating envelope, endlessly circulating, endlessly trapping heat. The direction of its spin and the speed of its rotation are not just curiosities, they're fundamental to why Venus became so different from Earth. But what might have caused that backward spin in the first place? The idea of a colossal impact remains compelling. In the early solar system, collisions were not the exception but the rule. Even small differences in timing could lead to dramatically different outcomes. A single strike from a body the size of a small moon could alter a planet's spin by dozens of degrees. If such an impact came late in Venus's formation, when its crust was already cooling, it could have disrupted its rotation without destroying it completely. Afterward, the planet's internal friction and tidal interactions with the Sun could have gradually slowed and reversed the rotation over eons. Another possibility is that Venus's dense atmosphere and the Sun's gravity entered into a kind of resonance. As the planet rotated, its thick air experienced solar heating that expanded and contracted unevenly, creating atmospheric tides. These tides would have exerted a drag on the planet's surface, gradually slowing its spin. Over immense timescales, this drag could have reversed the direction of rotation altogether. The result is what we see now, a slow, backward spin locked in a delicate balance with the Sun's gravitational pull. Venus's day is not arbitrary. It's the outcome of a long and complex dialogue between rock, gas and star. What makes this case so curious is that it challenges our sense of symmetry. We expect planets to follow patterns, to share behaviours, to fit within rules that make sense, but Venus doesn't. It obeys the same physics as every other world, yet the results look like exceptions. That's what makes it so revealing. Its retrograde rotation isn't a violation of natural law. It's an expression of how flexible those laws can be when chance and time are given enough room. The tilt of its axis, the length of its day, the direction of its spin, all are variations of the same universal process that shapes every planet. Venus simply followed its own path through those possibilities. There's also something hauntingly symmetrical about the relationship between Venus and Earth. Both worlds began with similar conditions. Both likely had oceans early on, perhaps even clouds of water vapour and mild climates. But while Earth stabilised, Venus tipped toward instability. Its closer distance to the Sun increased solar heating just enough to evaporate surface water, and that water vapour, a potent greenhouse gas, trapped more heat, accelerating the cycle. As the planet warmed, carbon dioxide was released from its rocks, amplifying the effect. The slow rotation made it easier for the atmosphere to redistribute heat globally, ensuring that no region ever cooled significantly. Within a few 100 million years, any hope of habitability had evaporated, leaving behind a world of crushing pressure and endless cloud. The spin and tilt of Venus are central to that story. A faster rotation might have encouraged a stronger magnetic field, perhaps slowing the loss of water to space. A greater tilt might have created more pronounced seasons, preventing the atmosphere from reaching uniform extremes. But Venus's particular combination of factors led it down a different path. Its backward rotation and near-zero tilt eliminated seasons and locked its climate into monotony. What was once possibly a temperate world became a furnace. The outcome is a living example of how sensitive planets are to their earliest motions. Even the way we see Venus today reflects its unusual spin. Its cloud tops reflect nearly 75% of the sunlight that reaches them, making the planet appear luminous in our sky. That brightness is enhanced by its slow rotation, which allows the clouds to build complex structures and persistent patterns. The winds at high altitude blow around the planet 60 times faster than the surface rotates, creating immense continuous vortices at the poles. From orbit, these look like giant double spirals, constantly reforming, driven by heat from below and motion from above. The planet's slow spin allows these features to evolve gradually, giving its atmosphere an appearance of calm even as it churns with ferocity. For scientists, Venus is both a warning and a mystery. It shows what can happen when feedback loops, born from small differences, are allowed to run unchecked. A planet almost indistinguishable from Earth at birth can diverge into something utterly alien, simply because of changes in spin, tilt, and atmosphere. Yet despite its hostility, Venus remains invaluable to understanding planetary evolution. Its retrograde rotation, its thick clouds, and its uniform climate help refine models of how worlds form, change, and sometimes fail. Every spacecraft that visits it, every radar image that maps its hidden surface, adds a new clue to the puzzle of motion and fate. When the first radar maps of Venus were made, scientists were stunned to find that the planet's surface rotated in the opposite direction to what was expected. For years there was debate over whether the data were mistaken, whether perhaps the instruments were inverted. But they weren't. The backward rotation was real, and with it came the realization that the solar system was even more varied than anyone had imagined. It wasn't a collection of identical spheres moving in harmony. It was a gallery of differences, each one an outcome of the same universal laws playing out in different contexts. If you think about it long enough, the curious case of Venus becomes almost poetic in its simplicity. Two planets formed beside each other under the same sun out of the same materials. One became blue, cool, and balanced, the other yellow, hot, and reversed. Their destinies diverged not because they were born different, but because of how they spun, how they tilted, and how they evolved under the subtle hands of gravity and heat. In every turn of Venus's slow day, in every backward sunrise, you can read the memory of ancient impacts, the drag of solar tides, and the delicate accidents that define worlds. Venus's story isn't finished. Its rotation may still be changing, however slightly. The thick atmosphere continues to redistribute momentum, the sun continues to tug on its orbit, and deep inside, slow convection may still influence its motion. The planet is in equilibrium, but not stillness. It continues to shift in ways we can barely measure. Even now, billions of years after its violent beginnings, it's still finding its balance. What makes this story so quietly powerful is that it's not unique to Venus. Every planet carries a similar narrative written in motion. Some are faster, some slower, some tilted to extremes. Each one is the product of countless interactions, impacts, tides, collisions, and chance. Venus simply shows us the extremes of what those interactions can produce. It's not the failure of order, but the full expression of it. A reminder that the same physics that made Earth habitable also has the power to make a world unlivable, depending only on how it begins to turn. Somewhere beneath those endless clouds, the surface of Venus remains unchanged, baked into permanence. No wind or rain reshapes its rocks. No erosion softens its craters. Time moves differently there, not in hours or seasons, but in cycles of pressure and heat that never break. The slow spin ensures that sunlight lingers long on every landscape, and the thick air ensures that no shadow cools quickly. It's a planet that lives in extremes of time, where rotation itself feels stretched. And yet, in that stillness, it keeps turning, endlessly, obedient to the same invisible law that keeps Earth spinning gently through night and day. If you look up and see Venus in the evening sky, that bright, steady light near the horizon, you're seeing more than reflection. You're looking at a world caught between order and anomaly, a planet that turned one way when everything else turned the other. Its glow carries both beauty and consequence. It's the shine of a world that reminds us how fragile motion can be, how small differences in spin and tilt can decide the fate of oceans, climates, and even the possibility of life. And while it seems serene from here, it is, at its heart, a monument to the power of accidents. The sculptor's hand still visible in every backward turn, every endless day, and every faint echo of what might have been if it had spun just a little differently. If every planet carries a quiet signature of its past, then Earth's signature is written in a gentle lean. It's easy to forget that our world doesn't sit upright in space. We imagine it spinning neatly, like a top on a perfect axis, but the truth is subtler. Earth is tilted, about 23.5 degrees from vertical. It's a small angle, hardly dramatic compared to the sideways roll of Uranus or the modest lean of Mars, but that small inclination changes everything. The light that falls on forests, the shifting length of shadows, the rhythm of planting and harvest, the way animals migrate and oceans breathe, all of it depends on that single tilt. The world we know, the climate we call home, the seasons that guide our calendars, all exist because our planet leans, neither too much nor too little, but just enough to let sunlight move. The origins of that lean trace back to the same collisions that shaped every planet. When Earth was young, still molten, still collecting the last fragments of rock from the surrounding disk, it was struck by an object large enough to change its orientation. That impact, the one that also formed the Moon, knocked Earth slightly off its vertical spin. The exact angle that resulted wasn't predetermined. It was the natural outcome of momentum exchanged in a single instant of contact. Yet that moment left the planet forever tilted, giving it the capacity for seasons, variation, and the long dance between sunlight and shadow that defines life's pattern here. When you look at Earth from space, you can see that tilt directly. The poles lean away from the orbital plane. During part of the year, the northern hemisphere angles toward the sun, and during another part the southern hemisphere does. That steady lean doesn't change much over short timescales. It's held in place by the Moon's stabilizing gravity, preventing the axis from wandering too wildly. Without the Moon, Earth's tilt could vary chaotically over millions of years, like Mars, whose angle of sunlight shifts enough to turn ice caps on and off. Instead, our planet wobbles only gently, a slow procession that takes about 26,000 years to complete one cycle. That quiet regularity has given stability to climate and allowed life to adapt to predictable rhythms. If you step back and imagine Earth's orbit as a ring of light around the sun, the tilt turns that ring into a pathway for contrast. When the north leans sunward, the days grow long above the equator's curve and light reaches far into high latitudes. When the south leans sunward, that same glow shifts across oceans and continents, carrying warmth elsewhere. Every place on Earth takes its turn facing the sun directly and then leaning away. The tilt ensures that no region holds the same relationship to light all year long. It shares warmth and cold, brightness and shadow, as if turning its face slowly between day and night on a planetary scale. That shift gives rise to the seasons, not because Earth moves closer to or farther from the sun, but because of how its axis directs sunlight. In June, the north tilts toward the sun, concentrating light and making days long. In December, it tilts away, spreading the same amount of sunlight over a larger area, reducing warmth and shortening daylight. The opposite happens in the southern hemisphere, where December brings midsummer and June brings winter. This alternating lean creates a continuous circulation of heat and air, driving monsoons, trade winds and jet streams. The tilt turns a static orbit into a dynamic world. It's a common misconception that the distance to the sun determines seasonal warmth. In truth, Earth is slightly closer to the sun in January than in July, yet the northern winter is cold because the sunlight falls at a shallow angle. The tilt matters more than the distance. Every beam of sunlight spreads over a wider area when it arrives obliquely, delivering less energy per square metre. That difference in angle is enough to sculpt climates, grow glaciers, and shift weather patterns. It is also what drives the cycle of life, the blooming of plants, the migrations of birds, the timing of hibernation. Every species on Earth has evolved under the influence of this predictable alternation between lean and light. If Earth had no tilt at all, the consequences would be profound. The sun would rise and set in nearly the same place every day, delivering equal days and nights across the globe. There would be no true seasons, no great migrations, no winter dormancy or summer abundance. The equator would remain hot, the poles cold, and the gradient between them would never shift. Atmospheric circulation might become locked into static patterns, With winds and rainfall confined to narrow bands, ocean currents would lose part of their global exchange. Without variation, ecosystems would stagnate. Life would adapt, of course, but it would be a simpler, less diverse life, shaped by constancy instead of change. If the tilt were greater, the opposite problem would emerge. With an angle of, say, 40 or 50 degrees, the poles would experience extreme summers of continuous sunlight and winters of unending darkness. The tropics would still be warm, but high latitudes would swing violently between melting and freezing. Ice sheets would grow and vanish in cycles far more intense than the gentle rhythm we know. In such a world, climates would be unstable. The range of habitable zones would shift rapidly, and life would struggle to keep pace. Our particular 23.5-degree angle sits delicately between those extremes, enough to create variety, but not so much as to cause chaos. That tilt doesn't remain completely fixed. It oscillates slightly over time, between about 22 and 24.5 degrees, in cycles that last tens of thousands of years. These slow changes, combined with the precession of the axis and variations in Earth's orbit, produce what scientists call Milankovitch cycles. Those cycles influence long-term climate trends, triggering ice ages and interglacial periods. Even though the variation is subtle, the cumulative effect shapes planetary history. When the tilt decreases, summers become cooler, allowing ice sheets to grow. When it increases, stronger summers melt them away. The rhythm of ice and warmth over hundreds of millennia is written in that slow, steady wobble. This delicate movement shows how even tiny changes in rotation can have massive consequences. A shift of a single degree alters how sunlight distributes across continents. That change influences how plants grow, how oceans circulate, and how carbon moves between air and sea. The tilt, though invisible in daily life, governs the entire system of feedbacks that keep Earth's climate within livable bounds. It also influences time in a human sense. The calendar we use, the holidays we mark, the agricultural cycles that once determined survival, all trace their origins to the tilt. Early civilizations built monuments aligned with solstices and equinoxes, because those moments mark the boundaries of light's journey, the return of the sun in winter, the longest day of summer, the balance of equinoxes. These were not arbitrary festivals, but reflections of planetary geometry. The tilt gave structure to culture, linking human ritual to cosmic motion. If you imagine Earth without that lean, much of our history would vanish. The migrations that followed changing seasons, the inventions of agriculture timed to rain and sun, even the psychological rhythm of the year would be different. The tilt doesn't just make seasons, it makes time feel cyclical, alive. It gives us reason to mark beginnings and endings, to anticipate change. In a way, it teaches impermanence, the understanding that light returns, that warmth follows cold, that every dark season ends. Scientifically, the reason the tilt persists so steadily is the presence of the moon. Our satellite's gravitational pull creates tides in Earth's oceans and even in its crust, and those tidal forces act like a stabilizing weight. They prevent the axis from wandering too far. Mars, lacking such a large moon, experiences wild swings in obliquity that have periodically transformed its surface. Earth's steady companion keeps our axis nearly constant, ensuring that the seasons shift predictably and that climate evolves gradually enough for life to adapt. The moon doesn't just light the night sky, it anchors the planet's balance. The interaction between spin, tilt, and orbit also defines how energy moves through the atmosphere. Because Earth is tilted, sunlight migrates north and south through the year, causing air and ocean currents to follow. This redistribution of heat drives the patterns we experience as weather. Monsoon rains, jet streams, trade winds, all trace back to that lean. Without it, the planet might still have circulation, but it would be simpler and weaker. The diversity of climates, deserts, forests, tundras, tropics, would shrink. The complexity of weather systems, and by extension ecosystems, owes its existence to the tilt's quiet guidance. On a more immediate scale, the tilt determines how long each of us experiences day and night. Near the equator, day length stays fairly constant. Near the poles, it changes dramatically. This variation has shaped how life evolved in different regions. Plants near the poles must grow quickly during long days and endure months of darkness. Animals migrate to follow the shifting line of sunlight. Human cultures adapted too, developing traditions and technologies to cope with these cycles. Every behavior tied to light and dark, work and rest, food and scarcity stems from a geometrical fact of the planet's spin. From a cosmic perspective, the tilt is a form of memory. It carries the imprint of the collision that once struck Earth, the gravitational interplay with the Moon, and the subtle tug of other planets over time. Yet for all its complexity, it remains graceful, not rigid, not chaotic, but balanced. The axis doesn't point exactly the same way forever, but its motion is predictable, a slow precession like the turning of a gyroscope. This balance between change and stability gives the planet resilience. Life thrives not because conditions are constant, but because they fluctuate within a range that remains familiar. The grace of Earth's tilt becomes especially clear when you compare it to planets that lack such moderation. On Mercury, the tilt is nearly zero, and the Sun hovers in the same position in the sky day after day. On Mars, the tilt varies so much that its climate has likely swung from icy to temperate and back again. On Uranus, the sideways rotation means one hemisphere can bake for decades, while the other freezes in darkness. Against these extremes, Earth's gentle lean feels like perfection. It produces enough change to keep the world dynamic, but not so much that it breaks equilibrium. The physical reason for this stability lies in the way angular momentum distributes across the planet-Moon system. The combined rotation and revolution create a gyroscopic effect that resists sudden changes in orientation. Over geological time, small torques from the Sun and other planets do influence Earth's motion, but only slowly. That slowness is our fortune. It allows evolution and adaptation to proceed at a pace that life can match. Rapid shifts would make survival harder. The tilt's grace is not in stillness, but in patience. If you could watch Earth over millions of years, you'd see the continents drift and oceans open, but the pattern of light and shadow would remain familiar. The solstices would shift gradually. The stars that mark north would change, but the rhythm of seasons would persist. The planet keeps its composure, balancing the energy it receives and radiates, turning gently through cycles that have repeated for nearly 4 billion years. The lean of our planet also affects how we perceive beauty. The golden slant of afternoon light, the length of twilight in summer, the low sun of winter casting long shadows, all of these visual qualities come from the tilt. Painters, photographers, and poets have drawn inspiration from it for centuries, often without realizing that they're celebrating a geometrical accident. The aesthetic rhythm of the year, the sense of change in color and temperature, the emotional texture of seasons, all are gifts of a 23.5-degree angle in space. Even our sense of time passing, the comfort in knowing that winter's chill will ease or that summer's heat will fade, owes itself to this geometry. The tilt ensures renewal. It ensures that no condition lasts forever. That balance between continuity and variation mirrors the balance of the planet itself, steady yet always in motion. When you think about it, the tilt is an answer to a larger question. How can a planet remain alive? Not biologically alive, but dynamically alive. Rotation gives rhythm, tilt gives contrast, orbit gives continuity. Together they create a system that breathes, circulates, and evolves. Without tilt, Earth would still spin, still orbit, but it would lack the pulse that makes climate, ecosystems, and even consciousness aware of change. The tilt is the heartbeat of the planet's experience of sunlight. As the Earth continues its steady path around the Sun, that heartbeat continues too. The light shifts south, then north, oceans swell and subside, winds follow warmth across latitudes. Everything on Earth responds in ways small and large, from the folding of leaves to the migration of entire species. The tilt may be invisible, but its influence is everywhere. When we look beyond our planet to others, we can see what the absence or exaggeration of tilt does. It teaches perspective. It reminds us that Earth conditions are neither ordinary nor inevitable. They are the outcome of ancient collisions, ongoing balances, and countless adjustments over time. The grace of our planet's tilt isn't an abstract notion. It's the very foundation of the world's livability. And as Earth keeps spinning, the Sun will continue tracing its slow path from solstice to solstice. The angle will remain, subtle but unwavering, guiding the rhythm of light that defines everything we know. It's a reminder that motion and balance are not opposites, they coexist. The planet's gentle lean is proof that the universe's most profound harmony can emerge from imperfection. A small angle, a quiet deviation, giving rise to everything that moves, grows, and changes under the sun. If Earth's tilt is a quiet rhythm that steadies its climate, Mars is the same rhythm played in a minor key, a little unstable, a little unpredictable, yet still echoing the same cosmic tune. The red planet has its own way of leaning and its own way of remembering. Where Earth's axis remains nearly constant, Mars wobbles. Its tilt shifts over time, swinging between gentle and extreme, rewriting its climate again and again. The memory of that motion is written across its surface, in dry riverbeds, frozen dunes, and the faint traces of ancient seas that once glittered in sunlight. Mars carries the scars of its tilt not as theory, but as landscape. Seen from space, Mars looks calm now, a quiet, rust-coloured world with thin air and a frozen calmness that feels almost peaceful. But the stillness is deceptive. Mars has lived through eras of transformation. There were times when its poles melted, its atmosphere thickened, and its sky turned blue with haze. There were times when it froze so deeply that carbon dioxide condensed directly from the air and formed frost on the plains. These changes were not caused by volcanic eruptions or impacts alone, but by something deeper, by the slow turning of its axis. The way its lean toward the sun has varied through time. Right now, Mars is tilted by about 25 degrees, not far from Earth's own angle. That means it has seasons, familiar in concept but harsher in expression. In summer, the pole facing the sun receives continuous daylight for months, heating the polar cap until it releases gas into the atmosphere. In winter, the opposite pole freezes as that gas condenses again. The planet breathes in this way, exhaling and inhaling carbon dioxide with the seasons. The air pressure on the surface rises and falls as ice turns to vapour and back again. Even though the atmosphere is thin, only about 1% of Earth's, this cycle dominates the planet's rhythm. But that tilt doesn't stay steady. Over hundreds of thousands and millions of years, Mars's axis can wander by tens of degrees. Unlike Earth, it has no large moon to hold it steady. The gravitational tugs from the Sun, Jupiter, and other planets gradually destabilize its orientation. In some epochs, the tilt may have reached as much as 60 degrees, enough to change everything about how sunlight falls across its surface. During those times, the poles would have received intense sunlight, melting ice and releasing vast amounts of vapour. The equator, on the other hand, might have cooled and frosted over. The whole planet would have reversed its thermal logic, turning polar regions into seas and mid-latitudes into deserts. Scientists have found clues to these ancient transformations. Orbital photographs reveal networks of dried river channels and valleys carved by flowing water. Radar instruments detect buried layers of ice beneath dust, arranged in patterns that match cycles of obliquity. These layers act like rings in a tree trunk, recording each shift in tilt as a distinct climatic era. Some layers are rich in ice, suggesting wetter periods. Others are dusty, signalling colder, drier times. It's as though Mars keeps a geological diary of its wobble, written in alternating bands of red and white. The mechanism behind this shifting tilt is complex but elegant. Every spinning body in space behaves like a gyroscope. Its axis tends to maintain direction unless acted upon by an external force. For Earth, the Moon's gravity provides a steadying hand, creating small precessions but preventing chaos. Mars, smaller and moonless in comparison, is more easily influenced. Jupiter, with its immense gravity, exerts a slow, persistent pull. Over time, that pull causes Mars's axial orientation to precess and oscillate. The planet's orbit is also slightly more elongated than Earth's, amplifying the effect. The result is a wobbling world, one that never fully settles into a single pattern of seasons. Imagine living there during one of its high-tilt periods. The sun would climb higher in the polar sky than it ever does today. Ice that has been frozen for millions of years would begin to sublimate, turning directly into gas and thickening the air. Temperatures would rise enough for liquid water to flow, at least for a while. The planet might experience rainfall or snowmelt, filling basins and carving valleys. Over thousands of years, it could resemble a cold, arid version of Earth. Cloudy skies, intermittent lakes, even glaciers retreating and advancing with the changing tilt. Then, as the axis leaned back again, the air would thin, the water would freeze, and the planet would return to stillness. Each cycle would erase much of what came before, leaving behind ghostly traces of its own climate memory. This rhythm of change gives Mars a kind of restless beauty. It's not static, even though it seems that way from afar. Its geography remembers motion. The vast northern plains may once have held oceans, the southern highlands ancient river networks. The poles still hold layered ice caps several kilometers thick, composed of water and carbon dioxide in alternating bands. These caps are like archives of the planet's climate, each layer recording a different orientation of the axis. The fact that these layers exist at all proves that the tilt has changed repeatedly, forcing ice to move, freeze, and reform in cycles that span millions of years. The connection between tilt and habitability is profound. When the tilt increases, sunlight reaches the poles more directly, releasing ice and raising atmospheric pressure. Under those conditions, liquid water could exist temporarily, at least in lower regions where pressure remains higher. If microbial life ever took hold on Mars, those warmer, thicker air epochs would have been its best chance. Conversely, when the tilt decreased, the poles remained frozen, the air thinned, and the surface became inhospitable. The planet may have swung between potentially livable and sterile states, its tilt acting as both giver and taker of opportunity. To understand how this works, scientists run long-term simulations of Mars's motion. These models extend back tens of millions of years, calculating how gravitational influences change its axial angle and orbital shape. The results show that Mars's tilt varies unpredictably beyond a certain timescale. Its future orientation cannot be known with certainty, because even small changes in orbit amplify over time, a hallmark of chaotic systems. It's not chaos in the sense of disorder, but in sensitivity. Every tiny influence matters. Jupiter's orbit, the pull of Saturn, the distribution of mass within Mars itself, all contribute to its ongoing wobble. There's a subtle elegance in how this instability shapes the planet's character. On Earth, the constancy of the tilt allows for stable evolution. On Mars, the variability ensures that nothing endures. Ice advances and retreats. Valleys fill and dry. Even the air itself thickens and fades. The planet is perpetually rewriting its climate, erasing old conditions and inventing new ones. In that way, Mars resembles a restless mind, always moving, never at peace, yet always holding faint memories of what came before. When spacecraft orbit Mars and look down on its surface, they see those memories preserved. Channels that meander for hundreds of kilometers, carved by flowing water long gone. Delta formations at the mouths of craters that once held lakes. Minerals that only form in the presence of liquid water. Each of these features testifies not just to water, but to a tilt that once allowed sunlight to reach where now it cannot. The geography itself becomes a map of the planet's past orientation. Even the atmosphere reflects this story. Today, Mars's thin air is dominated by carbon dioxide, with only traces of other gases. But during times of high obliquity, when the poles warm, more gas is released, thickening the atmosphere. The increase in pressure can raise temperatures slightly and enhance weather activity. Dust storms become larger, sometimes global, wrapping the entire planet in a reddish haze that lasts for weeks. These storms redistribute heat and further alter the planet's albedo, feeding back into the climate system. Over time, they contribute to how the tilt affects overall temperature and ice distribution. The lack of a stabilizing moon also influences Mars's internal behavior. Without the gentle tug that keeps Earth's core motion regular, Mars's internal dynamo faded early. Its magnetic field weakened, leaving its atmosphere vulnerable to solar wind. That loss accelerated the thinning of the air, which in turn made temperature swings more extreme. The changing tilt, then, interacts with this vulnerability. When the axis leans, sunlight can reach areas that were previously shielded, driving further sublimation of ice and loss of volatiles. It's a feedback loop that deepens over time, and yet, despite all this fragility, Mars endures. Its rotation remains steady enough to mark days, roughly 24.5 hours, close enough to Earth's that robotic explorers use similar clocks. It still spins on an axis, still tilts and precesses in ways that can be measured and predicted for thousands of years ahead. Its orbit remains stable enough to maintain seasons, even if those seasons differ from ours. In its own way, Mars has found balance within its instability. It doesn't collapse into chaos, it cycles through it. The memory of its wobble is not confined to ancient eras. Even now, the tilt continues to change slightly, altering how frost forms each winter. The polar caps grow and shrink annually, and the thickness of the atmosphere rises and falls with that rhythm. Each Martian year leaves a trace, a new deposit of ice, a new layer of dust, recording the subtle pulse of motion. The planet's ongoing story is written not in geology alone, but in geometry, in the slow movement of its axis through space. When we study Mars, we often project our hopes onto it. We look for water, for life, for a reflection of Earth. But perhaps its deeper lesson is about variability itself, about how a world can remain the same yet constantly change in orientation. How climate and habitability depend not only on distance from the Sun but on the angle of light. The wobble of Mars is a reminder that balance in the cosmos is rarely permanent. It's maintained through motion, through cycles that create and erase in equal measure. If you could stand on Mars during one of its great tilts, you might see a world that feels both alien and familiar. The horizon would glow faintly pink, the sun smaller than you expect, the sky perhaps hazy with suspended dust. The ground beneath you would be cold, yet the warmth of the sun would linger longer than it does now. Ice might trickle from crater walls. In the distance, you could see the gleam of frost receding as the tilt brought light farther north or south. The seasons would feel stretched, patient, ancient. Not the quick progression of months, but the slow breathing of millennia. That image captures what Mars truly represents. A planet caught between stability and change, forever remembering its own motion. Its tilt is not a flaw or an accident, but an identity. The oscillation that destabilizes its climate also defines its beauty. Every rock, every ridge, every frozen dune is a piece of a moving record. The planet may no longer have rivers, but it has memory, the quiet persistence of motion written into stone, and while we can't feel that wobble from here, We live under the same sky that once saw it begin. The same physics that makes Earth's seasons predictable makes Mars's chaotic. The same gravitational tugs that hold our world steady cause another to drift. It's a shared lineage of motion, a family of worlds each telling a different version of the same story. Mars just happens to tell the one about change, about how a world can lean and lean again, never quite finding stillness, yet never losing itself entirely. The next time you see Mars in the night sky, glowing softly like a distant ember, remember that you're seeing a planet mid-motion. Its axis is tilting even now infinitesimally, slowly changing how it faces the sun. Its climate is adjusting, its polar ice shifting, its air responding in cycles too vast for human time to grasp. It is the embodiment of motion remembered, the persistence of a wobble that began billions of years ago and will continue long after we are gone. The grace of its instability is that it never truly repeats itself. Each tilt brings a new pattern of light, a new rhythm of warmth and cold, a new version of Mars. And through those endless variations, the planet keeps spinning, keeps orbiting, keeps balancing between what it was and what it will become, carrying forward the memory of every turn that ever changed its face. Among all the planets that circle the sun, one dominates the system like a slow, steady heartbeat. Jupiter. Immense, radiant in reflected light, a world so vast that more than 1,000 Earths could fit inside it. Yet it spins with a speed that feels impossible for its size. Every 10 hours it completes a rotation, dragging its entire atmosphere, its storms and its magnetic fields around with it. It's the fastest spinner among the planets, though its size makes that rotation seem almost reluctant, as if a giant too large to move so quickly must do so by sheer force of momentum. Jupiter's motion is both graceful and immense, a world whose spin has shaped the architecture of the entire solar system. If the smaller planets are children of collisions and chaos, Jupiter is the elder, forged from gravity itself. It formed early, within the first few million years after the sun began to shine, before the disk of gas and dust had time to thin. The same process that shaped all planets, the collapse of matter, the conservation of angular momentum, worked at a different scale here. While the rocky worlds formed from dust and stone, Jupiter grew from gas. It started as a solid or icy core, perhaps 10 times Earth's mass, gathering surrounding hydrogen and helium, until it became massive enough to pull in everything nearby. That mass brought energy, and that energy brought rotation. The faster it grew, the more momentum it captured. By the time it stabilized, Jupiter's spin was locked in, a rapid, continuous rotation that would define its character forever. You might think such a fast spin would tear a planet apart, but gas giants are flexible worlds. They aren't solid spheres like Earth or Mars. Jupiter is composed mostly of hydrogen and helium, behaving more like a fluid than a rigid body. When it spins, it bulges at the equator and flattens at the poles, a shape called an oblate spheroid. The difference is dramatic. The planet's diameter at the equator is more than 10,000 kilometers, greater than from pole to pole. That distortion isn't weakness, it's balance. The spin provides centrifugal force that counteracts some of gravity's inward pull, helping maintain equilibrium across a body that never truly stops moving. Inside Jupiter, the story of that spin becomes even more complex. The planet doesn't rotate as one solid mass. Different regions move at slightly different speeds, a behavior known as differential rotation. The equator spins a bit faster than the higher latitudes, while the deeper layers may rotate differently still. This variation creates the distinctive bands and zones we see in its atmosphere, alternating stripes of light and dark, each representing massive jet streams moving in opposite directions. These bands aren't static patterns painted on the surface, they're living systems shaped by the planet's rapid rotation. Every stripe is a current of gas hundreds of kilometers deep, moving at hundreds of kilometers per hour, powered by the difference between sunlight, heat from the interior, and the momentum of the spin itself. When you look at Jupiter through a telescope, what you see isn't the planet's surface at all, but the tops of its clouds, layers of ammonia, water, and other compounds swirling in the upper atmosphere. Among them, storms rise and fall, some lasting for centuries. The Great Red Spot is the most famous, a vast, persistent storm larger than Earth, rotating in place like a permanent scar of motion. The existence of that storm is tied directly to Jupiter's rotation. The rapid spin amplifies Coriolis forces, which deflect moving air into spirals instead of straight lines. These forces allow storms to form, stabilize, and endure for unimaginable lengths of time. Without that rotation, the red spot might have dissipated long ago. The same spin that could be seen as violent also brings a kind of endurance, energy organized into structure rather than chaos. Despite its size and speed, Jupiter's tilt is almost non-existent. Its axis is inclined by only about 3 degrees. Compared to Earth's 23.5 or Mars's 25, that's nearly upright. It means Jupiter has no real seasons. The sunlight that falls on it barely changes throughout its 12-year orbit around the Sun. Its climate, if you can call it that, is nearly constant. Winds and storms driven by internal heat rather than by seasonal shifts in light. The smallness of that tilt might seem like a trivial fact, but it's a crucial clue to how the planet evolved. A gas giant with a little solid surface and immense self-gravity is difficult to disturb. The same collisions that tipped rocky planets barely affect one like Jupiter. It is too massive, too fluid, too bound together to lean. Its stability is almost absolute. In that sense, Jupiter's reluctance is not about speed, but about change. It spins quickly, but it resists alteration. Collisions that would have shattered smaller worlds barely dented it. Impacts still happen. Comet fragments fall into its clouds, flaring briefly before being absorbed. Yet none have ever changed its rotation in a measurable way. Its immense gravity acts like a shield, protecting the inner planets from stray asteroids and comets by drawing them in or flinging them out of the solar system. That gravitational dominance has shaped everything else's motion, including Earth's. Without Jupiter, our system would be unrecognizable. Many smaller bodies would have wandered inward long ago, striking the inner worlds far more often. The rhythm of stability we take for granted exists partly because Jupiter spins as it does, anchoring the solar system in its deep, constant gravity well. Inside Jupiter, the rotation sets the stage for forces we can't directly see. As the planet turns, its fluid interior moves, generating one of the strongest magnetic fields in the solar system. That magnetic field is enormous. It stretches millions of kilometers into space, creating a magnetosphere that envelops many of its moons. The field traps charged particles, producing intense radiation belts. It also interacts with the solar wind, creating auroras at the poles hundreds of times brighter than Earth's northern lights. These auroras flicker and twist with every pulse of the planet's rotation, a visual reminder that spin and magnetism are intertwined. Beneath those clouds and magnetic storms lies a region so extreme that ordinary definitions of matter blur. Deep within Jupiter, pressure increases until hydrogen behaves like a metal, conducting electricity. That metallic hydrogen, swirling under immense force, is what drives the magnetic field. And the rotation of the planet, the rapid, relentless turning of all that material, keeps the process going. It's a planetary dynamo on a scale almost beyond comprehension. Without that spin, the magnetic field would weaken, the radiation belts would fade, and the planet's entire interaction with space would change. This interplay between motion and magnetism extends to Jupiter's moons as well. The 4 largest, Io, Europa, Ganymede, and Callisto, each follow orbits shaped by Jupiter's rotation. The planet's gravity stretches and squeezes them, generating internal heat. Io, closest to the planet, experiences such intense tidal forces that its interior melts, driving constant volcanic eruptions. Europa, slightly farther out, maintains a subsurface ocean of liquid water beneath its icy crust, kept warm by the same tidal friction. Ganymede, the largest moon in the solar system, has its own magnetic field, induced by Jupiter's influence. The rotation of the giant governs the energy budget of its entire family. Without that spin, the moons would be colder, quieter, and lifeless. Instead, they are dynamic, alive with motion inherited from the giant they orbit. The speed of Jupiter's spin also reveals something about how quickly it formed. To achieve such a rotation, the planet must have accreted rapidly before the solar nebula's gas was dispersed by the sun's wind. That rapid growth preserved angular momentum in large amounts, locking it into the fast rotation we observe. The gas it captured carried spin from the surrounding disk, and because of the planet's enormous gravity, that spin could never be easily lost. In a way, Jupiter is the solar system's memory of the nebula's rotation, a preserved fragment of the original swirl that once encompassed everything. Despite its might, Jupiter's rotation isn't perfectly steady. Because the planet is made of fluid layers, the equatorial regions rotate once every 9 hours and 50 minutes, while the polar regions take slightly longer. Even the magnetic field rotates at a slightly different rate depending on depth. Measuring the true day of Jupiter isn't straightforward, because there's no solid surface to mark it. Scientists use the radio emissions from its magnetosphere to define the rotation period, using the planet's own magnetic heartbeat as a clock. In that sense, time on Jupiter is measured not by surface movement, but by magnetism, another expression of how deeply its spin defines its nature. When you observe Jupiter closely, you notice that its atmosphere is always changing, even though the overall structure remains. New storms appear, merge, and vanish. The Great Red Spot itself, though ancient, has been shrinking slowly in recent decades. Yet the underlying bands persist. The zonal winds continue. The rotation holds. There's something strangely meditative about that combination of constancy and motion. The planet moves too quickly for its size, yet too smoothly for chaos. Its rotation is power without haste, a kind of equilibrium through speed. From a distance, you might expect such a massive planet to dominate not only gravity but also light, yet it doesn't shine by reflection alone. Jupiter emits more heat than it receives from the Sun, a leftover from its formation, and from slow contraction under gravity. That internal heat contributes to the energy driving its atmospheric circulation, enhanced by rotation. The planet glows faintly in infrared, a giant still cooling, still radiating the memory of its birth. Its spin helps distribute that heat, maintaining patterns that have lasted since the solar system's dawn. If you think about Jupiter's influence, it extends beyond physics. Its sheer presence has inspired myths, art, and observation for millennia. The ancients saw it as a symbol of kingship and stability, a bright wanderer moving predictably across the night sky. Even then, its steadiness stood out. While Mercury flickered near the Sun, and Mars changed brightness with its orbit, Jupiter's slow, steady glow was constant. They didn't know it then, but what they were seeing was the outward sign of immense rotation, a planet turning so fast it appeared serene. Jupiter's lack of tilt means its day and night are almost perfectly symmetrical, its poles never leaning toward or away from the Sun. Yet within that symmetry lies subtle complexity. The planet's magnetic poles don't align perfectly with its rotational ones, creating a dynamic interplay between sunlight, spin, and field. The auroras flicker not because of seasonal changes, but because of how the planet's rotation drags magnetic lines through the solar wind. Even without seasons, Jupiter finds motion within motion. You might wonder what it means to call such a massive, fast-spinning world a reluctant spinner. The reluctance isn't about pace, it's about inertia. Once set in motion, Jupiter resists change with all its mass. It spins quickly, but it slows reluctantly. Its energy, stored in rotation, is so vast that only cosmic scale forces could alter it. The same principle that makes it turn swiftly also makes it stable. It's a paradox of motion, speed creating stillness, power creating calm. That calm, though, is deceptive. The outer atmosphere of Jupiter is a theatre of constant storms. Yet because the planet lacks a solid surface, there's no ground friction to slow them. Winds can last indefinitely, circulating in loops that endure for centuries. The rotation organises this turbulence into bands, preventing random chaos. In the depths below, convection moves heat upward, feeding the clouds. Every rotation mixes the gases, redistributing energy. The entire planet functions as a single dynamic system, its spin both a cause and a consequence of balance. If you could descend through those clouds deeper and deeper, you would feel the rotation differently. The winds would fade as you approached layers of denser gas. The sense of day and night would disappear, replaced by the steady glow of heat from below. Time would seem to compress, 10 hours passing like a moment. The planet's rotation would no longer be something you could witness. It would become something you inhabit, a background rhythm woven into the very structure of the world. Jupiter's role in the solar system is not only to spin, but to define space for others to move within. Its gravity sculpts orbits, captures asteroids, and anchors resonances that keep the system in order. The asteroid belt exists partly because Jupiter's influence prevents those rocks from merging into another planet. The orbits of many comets and small bodies are governed by encounters with it. Even Saturn's motion dances in subtle synchrony with Jupiter's, the two giants maintaining a long-term resonance that stabilizes their relationship. All of this stems from rotation and mass, the simplest forces in the universe, producing the most complex results. In the grand scheme, Jupiter represents permanence through motion. Its spin has barely changed in billions of years. It will continue long after the inner planets have evolved beyond recognition. When the Sun expands into a red giant, Jupiter may survive, orbiting farther out in cooler light, still rotating, still holding onto its moons. Its rotation will slow eventually, over immense timescales, as tidal forces exchange energy between planet and satellites. But even that slowing will be glacial, almost imperceptible. The giant will remain what it has always been, a guardian of motion, a reminder of how gravity and spin can shape not only a world but an entire system. If you look at Jupiter tonight, you'll see it shining bright and steady in the sky, its light unwavering. Through a telescope, you might glimpse the 4 largest moons lined up beside it, changing positions night after night as they orbit. You can imagine them moving within its invisible gravitational embrace, responding to a rotation so vast that it keeps time for them all. The planet turns, they respond, and the solar system continues its rhythm. It's the same rhythm that began in the swirling disk of gas that made everything we know, a motion too ancient to measure, too consistent to end. In Jupiter's endless spin, you can see what the universe values most. Not stillness, not chaos, but continuity. The planet's rotation is a bridge between extremes, fast but steady, massive but balanced. It carries the same momentum that once swirled through the newborn sun's cloud, the same pattern of turning that gave rise to every orbit, every moon, every moment of motion in the cosmos. It's not just the largest planet, it's the anchor of a rhythm that holds the solar system together, a reluctant spinner only in the sense that it could never stop, not without undoing everything that followed its first turn. If Jupiter is the solar system's anchor, then Saturn is its quiet echo, a world that spins almost as swiftly, shines just as steadily, and yet wears its motion like a piece of jewellery. From a distance, Saturn looks serene, a golden lantern suspended in the darkness, surrounded by its bright, delicate rings. But behind that beauty lies a deep motion, one that governs the planet's balance, its symmetry, and its place in the solar system's rhythm. Saturn spins rapidly, tilts elegantly, and glows with a calm that belies its restless nature. It's a planet that seems composed, yet every feature of it, from the rings to the atmosphere to the tilt of its axis, tells the story of motion preserved through time. When you first see Saturn through a telescope, it's hard to believe it's real. The rings look fragile, almost weightless, like they might vanish if you blinked. But they are not fragile. They are ancient and dynamic, shaped and maintained by Saturn's rotation. The planet completes one full spin in a little more than 10.5 hours, only slightly slower than Jupiter, despite being smaller and less massive. That rotation, combined with its lower density, gives Saturn an even greater equatorial bulge, a visible flattening that you can almost see in photographs. The poles are pulled inward by gravity, the equator pushed outward by momentum, giving the planet an elegant symmetry that feels both deliberate and effortless. Inside, Saturn is a world of layered hydrogen and helium, just like Jupiter, but with its own proportions and temperature gradients. It too emits more heat than it receives from the Sun, though for a different reason. As the planet cools, helium droplets separate from hydrogen deep within, falling slowly toward the core. This helium rain releases energy, maintaining internal warmth long after formation. The rapid spin helps distribute that heat, keeping the atmosphere in constant motion. Bands of clouds encircle the planet, parallel and continuous, driven by winds that reach more than 1,000 kilometers per hour. The patterns look peaceful from afar, but they are the visible expression of immense kinetic energy. The planet's rotation turned into weather. The tilt of Saturn's axis is about 26.5 degrees, close to Earth's own. That tilt gives Saturn true seasons, each lasting more than 7 years because of its long 29-year orbit around the Sun. As the planet moves through its cycle, one hemisphere tilts towards sunlight while the other falls into shadow. Over those years, the rings, thin, flat, and aligned with the equator, change their appearance dramatically from our vantage point. Sometimes they open wide, showing their full span. Other times they appear as a razor-thin line, nearly invisible. That slow oscillation of brightness, driven by Saturn's tilt, is one of the most graceful phenomena in the solar system. It's as if the planet is breathing, turning its face gently toward and away from the Sun in an unhurried rhythm that has lasted for billions of years. Those rings, for all their beauty, are not solid. They are made of countless particles, chunks of ice, dust, and rock, ranging in size from grains smaller than snowflakes to boulders the size of houses. Each one orbits Saturn independently, following the same laws of motion that govern moons and planets. The rotation of the planet helps maintain their structure. The gravity of Saturn's many moons, working in concert with the planet's spin, creates resonances that shape gaps and edges within the rings. The result is a system of dynamic stability, where chaos and order coexist perfectly. Every particle in those rings is a reflection of Saturn's balance, spinning around a world that itself spins in quiet perfection. No one knows exactly how the rings formed. They might be remnants of a moon shattered by tidal forces long ago, or leftover debris from the planet's formation that never coalesced into a single body. Whatever their origin, their persistence depends on motion. Without Saturn's rapid spin and strong gravitational field, the particles would eventually drift away. But the planet's rotation creates a bulge that influences their orbits, ensuring that the rings remain thin, aligned, and stable over immense spans of time. They are, in a sense, the visible boundary between the planet's rotation and the outer silence, a reminder that even in stillness, movement defines everything. The tilt of Saturn doesn't only give it seasons, it also affects how sunlight interacts with the rings. During equinoxes, when the sun crosses the ring plane, the shadows cast by the rings fall in delicate lines across the planet's surface, revealing subtle details of both the rings and the atmosphere. These shadows move with precise timing, tracing the planet's rotation and marking the slow progress of its orbit. In those moments, the geometry of light and motion becomes visible. The planet's spin, tilt, and orbit combine into an intricate display of balance, like a cosmic clock keeping perfect time. Despite its serenity, Saturn is a world of storms. Its atmosphere, though less colourful than Jupiter's, contains massive cyclones and long-lasting vortices. At its north pole lies one of the most extraordinary features in the solar system, a hexagonal jet stream, six-sided and perfectly shaped, encircling a vast polar storm. This hexagon is not a static object. It's a standing wave formed by the planet's rotation and atmospheric flow. The entire pattern turns with the planet, maintained by the balance of wind speed, pressure, and rotation. The geometry feels almost impossible, yet it arises naturally from motion. Only a planet spinning as Saturn does could sustain such a precise and stable structure in its atmosphere. Beneath the clouds, the same motion continues. Saturn's interior layers rotate at slightly different speeds, creating shearing flows that transport heat and shape weather systems above. The deeper regions, where hydrogen becomes dense and metallic, may rotate more uniformly, acting as the foundation for the magnetic field. Saturn's magnetic field, though weaker than Jupiter's, is remarkably symmetrical, almost perfectly aligned with its rotation axis. This near-perfect alignment puzzled scientists for years because it defies expectations. Magnetic fields usually tilt relative to spin. The reason may lie in Saturn's internal rotation, which is smoother and more evenly distributed than other planets. The symmetry of its magnetism mirrors the symmetry of its spin. This alignment contributes to Saturn's calm personality. The planet doesn't produce the same violent radiation belts as Jupiter, nor the same intense auroras, though it has both in milder forms. Its auroras glow softly at the poles, responding to the flow of charged particles from the solar wind and from its moons, especially Enceladus, which vents water vapour into space. The connection between the planet's spin, its magnetic field, and its moons forms a delicate network of interactions, each rotation subtly influencing another. The entire Saturnian system behaves like a miniature solar system, with its own rhythms, harmonies, and gravitational music. Among Saturn's moons, Titan stands out, a world larger than Mercury, wrapped in a thick atmosphere. Titan's slow orbit, tidally locked to Saturn's rotation, means it always shows the same face to its parent planet. The gravity of Saturn pulls on Titan's atmosphere, creating winds and tides that echo the motion of the giant itself. Inside Titan's haze, rivers of methane and ethane carve channels that mirror the same geometry as rivers on Earth. Every drop, every flow, is guided indirectly by Saturn's spin, the source of the energy that shapes its weather and drives its tides. Even far from the Sun, the planet's rotation gives rise to movement and balance among its companions. Saturn's influence extends even farther, affecting the orbits of other planets through gravitational resonance. Its rhythm of revolution and rotation aligns subtly with Jupiter's, forming patterns that stabilize the solar system. Without these resonances, planetary orbits might drift into instability over billions of years. The giant planet's spins, seemingly isolated motions, actually help preserve the order of everything else. It's a quiet form of stewardship. Motion maintaining motion. There's something deeply peaceful about Saturn's combination of speed and calm. It spins rapidly, yet that speed creates balance rather than chaos. It tilts, yet that tilt produces grace rather than disorder. Its rings, so thin they're almost non-existent, are the visible trace of this equilibrium. Each particle within them orbits according to laws that never change, yet the collective result looks delicate, transient, and alive. The whole system seems poised between fragility and endurance, shimmering softly in the light of the distant sun. From our perspective, Saturn's golden colour comes from sunlight scattering through its atmosphere, filtered by clouds of ammonia and hydrocarbons. That gentle hue reinforces its sense of poise, warm, steady, neither cold nor burning. The planet doesn't display the violent contrasts of Jupiter or the desolate red of Mars. It radiates moderation, as if its spin has reached a natural speed that satisfies gravity, temperature, and balance all at once. In a universe where most things lean toward extremes, Saturn occupies the middle ground. The origin of its rings and tilt may even be connected. Some studies suggest that Saturn once had another large moon, which was lost in a slow, orbital decay. As that moon spiraled inward, tidal forces tore it apart, forming the rings, and at the same time altered the planet's tilt. If that's true, then Saturn's most beautiful feature, the rings that make it iconic, also mark a record of change, a graceful aftermath of destruction. The poise we see now may be the equilibrium that followed a moment of imbalance. A return to harmony after motion reshaped everything. If you could stand on one of Saturn's moons and watch the planet rise above the horizon, you'd see a disk vast enough to fill half the sky. The rings would arch overhead like bridges of light. You could watch their shadows slide slowly across the planet's clouds, tracing the hours of its fast rotation. You'd see storms drift along the equator and clouds shimmer gold in reflected light. Even from that distance, you'd feel that you were witnessing motion made visible. Gravity, spin, and tilt woven together into something endlessly fluid and perfectly composed. The rhythm of Saturn's day is relentless but not harsh. 10.5 hours to spin once. 29 Earth years to complete a journey around the Sun. Each day is quick, each year slow. That ratio gives the planet its quiet steadiness. The rapid spin prevents extremes of temperature, while the long orbit makes seasonal changes subtle and drawn out. It's as if time itself moves differently there, swift in one sense, languid in another, both balanced in the same breath. Saturn's magnetosphere, shaped by its rotation, extends millions of kilometers into space, encompassing its entire family of moons. Within that magnetic field, charged particles flow along invisible lines, connecting the planet to its satellites. Every 10.5 hours, those lines twist, realign, and generate bursts of radio waves detectable from Earth. These emissions serve as a clock for scientists, marking the planet's rotation deep below its clouds. Saturn keeps time through motion, its rotation broadcasting a signal that travels across the void, a steady pulse of movement, too low for the ear but perfect for instruments to hear. Even after decades of study, Saturn's rotation remains difficult to define precisely. Because the planet's magnetic field is so symmetrical, it doesn't produce a strong external marker for rotation like Jupiter does. The winds in the atmosphere move at varying speeds, the deep interior turns differently, and the magnetosphere drifts slightly with solar influence. Every measurement of Saturn's day differs by minutes, as if the planet resists being timed too exactly. Its poise includes an element of mystery, a subtle refusal to yield all its rhythm to our understanding. In many ways, Saturn represents the middle note in the solar system's harmony. It sits between Jupiter's raw power and Uranus's peculiar tilt, between the inner planet's solidity and the outer one's cold remoteness. Its balance is its defining trait, fast but not turbulent, massive but not crushing, radiant but not overwhelming. The golden colour, the steady tilt, the intricate rings all speak to equilibrium. Saturn moves neither too quickly nor too slowly. It doesn't dominate through force, it leads through balance. When you look at it through a telescope, shimmering softly against the blackness, you're seeing more than reflected sunlight. You're seeing geometry, physics, and time in their purest collaboration. You're seeing the way motion can become symmetry, and how speed can translate into serenity. Saturn doesn't demand attention. It invites stillness. It reminds you that even the grandest forces in the universe can express themselves with gentleness, and somewhere, beneath those golden clouds, hydrogen still swirls around a small dense core, spinning endlessly, maintaining the planet's rhythm. The winds blow, the rings shimmer, the axis leans, and the planet continues its turn, constant, poised, eternal in its own quiet way. The grace of Saturn's motion isn't in what it does, but in how effortlessly it continues. It's the art of movement balanced so perfectly that it becomes indistinguishable from peace. Far beyond Saturn's glowing rings, where sunlight weakens to a pale whisper, and space begins to feel genuinely empty, another world turns in a way that almost defies expectation. Uranus, a planet so quiet, so distant, that for centuries it remained unseen by human eyes, blending with the slow shimmer of faint stars. When telescopes finally revealed it, astronomers discovered a pale green-blue disk, small and still, circling the sun in calm indifference. But beneath that quiet appearance lies one of the strangest motions in the solar system, a planet that rolls on its side, spinning like a tilted barrel as it moves along its orbit. If Jupiter and Saturn embody balance and order, Uranus is the reminder that the universe always leaves room for exceptions. Its axis is tilted by about 98 degrees, which means it doesn't simply lean, it lies almost completely flat. The poles point almost directly toward the Sun during parts of its orbit, and for decades at a time, one hemisphere basks in continuous sunlight, while the other drifts in unending night. No other planet in the solar system behaves quite like this. Its strange rotation makes it both a curiosity and a key to understanding how motion can evolve into something unpredictable yet still lawful. From a distance, Uranus looks peaceful. Its faint bluish colour comes from methane in its upper atmosphere, which absorbs red light and reflects the blue-green part of the spectrum. It has no sharply defined cloud bands like Jupiter or Saturn. The planet's surface appears smooth, uniform, even serene, as if its tilt had calmed it. But that calm is deceptive. Beneath those bland clouds, Uranus is every bit as dynamic as its larger siblings, only quieter in expression. Winds rush through its atmosphere at speeds exceeding 800 kilometers per hour. Thin layers of haze drift and shift, revealing storms that appear and vanish within days. The entire planet turns slowly, completing one rotation in about 17 hours, yet the sense of time there feels distorted by the long seasons that come from its extraordinary tilt. Imagine standing on one of Uranus's moons. The planet would fill the sky, glowing softly in aquamarine hues. If you were near one of the poles during summer, the sun would hang almost motionless above the horizon, tracing a small circle that never sets. The light would remain steady for decades. Then, as the planet moved through its 84-year orbit around the sun, that same pole would slowly turn away, plunging into a winter that would last equally long. Half the planet would be bathed in light for years, half would rest in darkness. Only at the equinoxes, once every 42 years, would sunlight briefly cross the equatorial regions, illuminating the ring's edge-on and creating a fleeting balance between day and night. This sideways rotation remains one of the most intriguing mysteries in planetary science. How did a planet end up turning on its side? The simplest explanation is the same one that shaped so many other peculiarities in the solar system: a massive collision. During its formation, Uranus may have been struck by a body nearly as large as Earth, an impact so powerful that it tipped the planet over without destroying it. The debris from that event may have later coalesced into the planet's moons and faint rings. Another theory suggests multiple smaller collisions occurred, each contributing to the cumulative tilt. In either case, the cause was likely violence transformed into balance, a sudden moment of chaos that left behind a new kind of order. Whatever its origin, the result is profound. The tilt doesn't just change how Uranus looks, it changes everything about its environment. Because the poles spend so long facing or turning away from the sun, the flow of energy through its atmosphere differs radically from that of any other planet. During polar summers, sunlight pours onto one hemisphere for decades, heating the upper atmosphere. During winters, that same region cools under an extended night. The long intervals of illumination and shadow create deep atmospheric currents, moving heat and gases in slow, complex cycles. It's a rhythm so vast that no spacecraft or telescope has yet witnessed a full Uranian year from start to finish. Beneath the atmosphere lies a world that is neither solid nor gaseous in the way we usually imagine. Uranus, like Neptune, is classified as an ice giant, composed mainly of water, ammonia and methane in slushy, pressurized forms. The planet likely has a rocky core surrounded by layers of compressed fluids, thick enough to blur the line between solid and liquid. In that interior, the rotation behaves differently from the outer atmosphere, producing one of the strangest magnetic fields ever observed. Unlike Earth's, which is centered near the planet's core and aligned with its axis, Uranus's magnetic field is both offset and tilted at nearly 60 degrees relative to its rotation. The magnetic poles wander across the surface, creating auroras that appear in unpredictable locations. This uneven magnetism may result from currents flowing in layers far above the core, a magnetic field generated not deep inside but closer to the surface, another oddity born from the planet's sideways spin. Because of this unusual geometry, Uranus's magnetic field behaves chaotically as it rotates. The field lines twist and untwist, interacting with the solar wind in constantly shifting ways. Each rotation exposes different parts of the magnetosphere to sunlight, producing bursts of radiation and energy at irregular intervals. To an observer, it would seem as if the planet's magnetic heartbeat never settles into a steady rhythm. The tilt turns what might have been a simple, symmetrical system into something dynamic and evolving, a magnetic world that refuses to be predictable. For all its peculiarities, Uranus remains a model of balance in its own right. Its spin is steady, its orbit circular and stable, and its temperature remarkably uniform. The entire planet hovers at around minus 200 degrees Celsius, with little variation from equator to pole. This evenness might seem surprising given its extreme tilt, but it likely results from the slow exchange of heat between hemispheres over the course of its long seasons. When one pole faces the sun, it stores warmth that will later drift toward the darkened half as the cycle reverses. The planet's own faint internal heat, much weaker than that of Jupiter or Saturn, helps smooth these transitions further. It is as though Uranus has found a quiet equilibrium between light and dark, motion and stillness, energy and cold. Its rings, faint and narrow, echo that same quiet character. Discovered in 1977, they are darker and smaller than Saturn's, made mostly of dust and small particles. Yet they too are shaped by the planet's rotation and tilt. Because the rings lie along the equatorial plane, they orbit perpendicular to the sun's rays for most of Uranus's year. During equinoxes, when sunlight briefly shines edge on, the rings cast delicate lines of shadow across the planet's atmosphere, much like Saturn's do but on a subtler scale. These alternating shadows reveal how precisely the rings and planet move together, how the tilt organizes light into patterns that appear and vanish in cycles too long for any human lifetime to fully witness. The moons of Uranus follow this same tilted geometry. All 27 of them orbit roughly along the planet's equator, meaning they too revolve in a plane almost perpendicular to the sun. Each moon experiences the same extremes of light and darkness as the planet itself, decades of day followed by decades of night. The largest, Titania and Oberon, have surfaces marked by canyons and cliffs, suggesting past geological activity. Others, like Miranda, display fractured terrains so strange they look as if the moon has been shattered and reassembled. These features hint at ancient tidal stresses, moments when the planet's rotation and the Moon's orbits interacted to create internal heat. Even in this distant region of the solar system, motion remains the quiet architect of everything. From a scientific perspective, Uranus is a reminder that planetary systems are not built on symmetry alone. The same physical laws that gave Earth its comfortable tilt and Jupiter its near-vertical axis also allow for worlds turned completely sideways. The equations don't change, only the initial conditions do. A single collision, a small imbalance in angular momentum can send a planet into a new configuration that lasts for billions of years. What looks like an anomaly is simply another valid solution to the same problem: how a body moves when left to the will of gravity and inertia. If you were to watch Uranus over the course of its long orbit, you would see a planet that doesn't rise and set in the familiar way. The Sun doesn't travel from horizon to horizon there, it circles around the poles. At the equator, the concept of sunrise and sunset almost disappears. The sky changes not through daily cycles, but through epochs of light and darkness. It's a place where time stretches, where rotation and orbit merge into one slow turning of perspective. The tilt makes every season a generation long, every transition between them a quiet unfolding measured in decades. This unusual rhythm also affects the way Uranus interacts with the rest of the solar system. Its sideways orientation changes the way it responds to the Sun's gravity and the subtle tugs from other planets. Over long periods, those influences cause the direction of its axis to precess, to slowly trace a circle in space. The rate of this precession is different from that of the other planets, making Uranus's long-term evolution difficult to predict precisely. Even so, the system remains stable. Its odd tilt hasn't caused chaos, it has simply created its own version of order, governed by the same steady principles that keep every other planet in motion. When Voyager 2 flew past Uranus in 1986, the only spacecraft ever to visit, it saw a world turned sideways, illuminated by a sun low on the horizon. The images showed a bland face at first, pale and nearly featureless. But as data came in, a more complex picture emerged. Temperature gradients, subtle cloud layers, magnetic fields misaligned with rotation, and a ring system so dark it absorbed most of the sunlight that reached it. For scientists, it was a revelation. A planet once thought simple and inert was in fact intricate and alive with invisible motion. The sideways spin was not a quirk, it was a key. It showed how deeply rotation shapes not only a planet's weather, but its entire identity. Today, telescopes and space probes continue to study Uranus from afar, searching for signs of change as the planet moves slowly through its orbit. Each observation reveals something new: faint storms appearing at the edges of sunlight, shifts in brightness that suggest deeper atmospheric layers coming into view, hints of seasonal transformation as one pole begins to dim and the other brightens. The planet changes, but so gradually that no single observer can see its full cycle. It's the kind of world that asks for patience, that teaches perspective through time. There's a quiet irony in how Uranus, the most tilted of the planets, maintains some of the most stable conditions. Its axial extremes create balance through duration. Its sideways spin, rather than producing chaos, produces constancy. The cold remains cold, the winds continue to blow, and the geometry of its orbit remains nearly unchanged. It's as if the planet found peace in being different, a world that doesn't resist its oddity but embraces it as equilibrium. When you think of it, that's the essence of planetary motion. Every world carries its own form of balance, defined not by symmetry, but by persistence. Jupiter's rapid spin, Saturn's golden tilt, Earth's gentle lean, Venus's backward turn, all are solutions to the same dance. Uranus just happens to perform its steps lying on its side, slowly rolling through space, unhurried, unmoved by convention. The sleeping giant, tranquil in its tilt, is not an anomaly but a testament to nature's willingness to explore every possible rhythm. If you could drift beside it, you might not notice its rotation at first. The surface would look unchanged for hours, the faint light of the sun casting an even glow across its smooth clouds. Only by watching the subtle drift of shadows or the motion of a distant moon would you realize that the planet is turning, slowly, endlessly, sideways through the cold. It doesn't spin in defiance of the rest, it spins in complement, filling the spectrum of what motion can be. Its stillness is only an illusion born of distance and light. Up close, Uranus is never still. It moves with the same purpose as every other world, carrying forward the ancient energy of the nebula that birthed it, preserving through its peculiar angle the memory of all that came before. In the faint light of the outer solar system, Uranus continues its long, slow turn, one pole now facing the sun, the other gazing into darkness. The line between day and night is not a frontier but a curve that drifts endlessly. It's a planet suspended between illumination and shadow, between ordinary and extraordinary, a world that proves even the strangest motions can find their own quiet grace. And as it rolls onward through its 84-year journey, the sideways spinner keeps time in its own way, not through the rising and setting of the sun, but through the patient, eternal act of turning. Beyond Uranus, where sunlight fades to a faint whisper, and the warmth of the inner solar system becomes a distant memory, Neptune turns in the deep cold with remarkable consistency. It is the farthest major planet from the Sun, orbiting on the edge of a realm that blends into the interstellar dark. From here, the Sun is no more than a bright star, yet Neptune still spins, still shines faintly in its blue hue, still participates in the ancient rhythm that binds all worlds. Its rotation, though quick and powerful, feels deliberate, not rushed, not chaotic, but steady, as if the planet has long since accepted its role as the outermost guardian of motion. Neptune is often described as mysterious, but that mystery isn't in what we see, it's in what we can't. The planet's atmosphere is made mostly of hydrogen, helium and methane, like Uranus, but its colour is a deeper blue, richer and more vivid, a result of how methane absorbs red light and how unknown elements scatter sunlight within its clouds. It's a blue that looks alive, even at billions of kilometres away, a colour that feels cold yet dynamic, quiet yet full of energy. The planet's disk appears calm from afar, but the truth is far different. Neptune holds the fastest winds in the solar system, storms that race around it faster than sound. And all of this energy flows from a planet that lies where the sun's warmth should have almost no power at all. Its speed is astonishing. Neptune completes one rotation every 16 hours, nearly the same as Uranus, though its mass and internal structure differ. The planet's equator bulges slightly, but not as dramatically as Saturn's or Jupiter's, suggesting a more uniform distribution of density beneath the clouds. Still, the rotation is fast enough to organise the entire atmosphere into bands and currents. If Jupiter's clouds are majestic and Saturn's are elegant, Neptune's are restless. Narrow streaks and bright white patches that appear and vanish as storms form and dissolve. The rotation drives all of it, feeding motion into a world that would otherwise be still. The Great Dark Spot, first seen by Voyager 2 in 1989, is one of the most striking results of this motion. It was a storm roughly the size of Earth, swirling in the planet's southern hemisphere with winds reaching nearly 2,000 kilometers per hour. Unlike Jupiter's long-lived red spot, Neptune's storms appear and fade within years, sometimes months, replaced by new vortices elsewhere. The transient nature of these storms reflects the planet's deep energy balance. Neptune emits more heat than it receives from the Sun, powered by the slow release of leftover formation heat, and possibly by gravitational contraction. This internal warmth rises through the atmosphere and meets the rapid spin, creating the fastest and most volatile weather in the solar system. For all that speed, Neptune's tilt is surprisingly modest, about 28 degrees, slightly more than Earth's. That means it experiences seasons, though each lasts about 40 Earth years. These long seasons unfold gently, with subtle changes in cloud patterns and atmospheric brightness, as sunlight shifts from one hemisphere to the other. Unlike Uranus, which rolls on its side, Neptune's rotation remains upright enough for its poles and equator to maintain a steady dialogue of light. The planet's magnetic field, though oddly tilted and off-centre like Uranus's, behaves in a more predictable way, producing bright auroras at unexpected latitudes. These auroras flicker not with the sun's rhythm, but with Neptune's own, driven by rotation and the deep electric currents moving within. Inside, Neptune is built like Uranus, yet behaves differently. It too has a small rocky core surrounded by layers of icy materials and dense gases, but its interior heat seems more active. The planet radiates about twice as much energy as it receives, suggesting a dynamic interior that still stirs after billions of years. The rotation enhances this internal convection, helping to distribute warmth and maintain the planet's magnetic field. In a sense, Neptune is not cold at all. It's a slow-burning ember, releasing energy in patterns so vast that only its motion can express them. If you could descend through the planet's atmosphere, the experience would feel like moving through layers of texture rather than through space. The upper clouds, made of methane ice, glide at supersonic speeds. Below them, ammonia and hydrogen layers mix under pressure. Deeper still, the gases compress into exotic fluids, electrically conductive and turbulent. The rotation carries these layers in massive belts, flowing eastward and westward around the planet. There's no surface, no solid ground, only a gradual transition from gas to fluid, from air to ocean, from light to darkness. Down there, rotation is not something seen, but something felt, like a slow vibration in the fabric of matter itself. Neptune's steady whirl is not isolated. Its gravity influences a whole family of companions, most notably its largest moon, Triton. Triton is unique among large moons because it orbits Neptune in the opposite direction of the planet's rotation, a retrograde orbit that suggests it was captured rather than formed in place. Long ago, Triton may have been a separate world, perhaps a dwarf planet from the Kuiper Belt, drawn in and tamed by Neptune's pull. That capture would have been violent, producing heat through tidal forces that melted Triton's interior and possibly created its current surface of frozen nitrogen and methane. Even now, Neptune's gravity flexes the moon's crust, driving geysers that vent plumes of nitrogen gas into space. The dance between Neptune's rotation and Triton's reverse orbit is a reminder that motion never ends cleanly. It continues to negotiate, to balance, to reshape. The capture of Triton also likely disrupted Neptune's original satellite system, scattering smaller moons and perhaps altering the planet's tilt slightly. Today, Neptune's other moons, most of them small and irregular, orbit in a variety of planes, testifying to a past filled with gravitational encounters. Yet the planet itself remains steady. Its spin, set billions of years ago, continues without significant change. The outermost world of the major planets holds its rotation with quiet authority, a constant in a region defined by cold and distance. From a dynamic standpoint, Neptune's rotation has other consequences. It helps generate one of the strongest magnetic fields per mass in the solar system, influencing space far beyond the planet's physical body. This magnetic field interacts with the solar wind, creating a magnetosphere that trails behind the planet like a vast comet's tail. Because the magnetic axis is tilted nearly 47 degrees from the rotational axis, the field wobbles as the planet turns, sending rhythmic waves of energy outward. Every 16 hours, the orientation of that field flips relative to the Sun, producing fluctuations that ripple through the outer solar system. Even here, in the cold frontier where sunlight barely reaches, motion creates connection, The stability of Neptune's spin stands in quiet contrast to the turbulence of its weather. While winds rage and storms appear and fade, the overall rhythm of rotation stays precise. The planet's day length varies only slightly between atmospheric latitudes, despite its fluid nature. The deep interior likely rotates at a near constant rate, anchoring the upper layers in a consistent frame. It's a kind of anchor in motion, rapid enough to sustain energy, stable enough to maintain balance. The interplay between speed and steadiness defines Neptune's character, just as surely as its colour defines its appearance. The atmosphere's violent winds paradoxically create a sense of peace when viewed from afar. Because everything moves so fast, individual details blur into smoothness. The bright spots and streaks shift too quickly for the human eye to follow, giving the impression of serenity. It's like watching waves from a distance, calm at scale, chaotic in detail. This blending of motion and stillness is Neptune's signature. It is the outermost planet, but not the quietest. Its energy comes from within, a persistent heat transformed into winds and storms, moderated by rotation until it feels almost like breath. Triton, orbiting against this motion, introduces a subtle counterpoint. Its retrograde path gradually steals energy from Neptune's rotation through tidal friction, causing the moon to spiral slowly inward. In billions of years, it may cross the planet's Roche limit and be torn apart, forming a ring system that would briefly rival Saturn's. If that happens, Neptune will inherit a halo of its own, a new structure born from the remnants of its captured companion. Even that distant event will be governed by rotation, tides, spin, and balance continuing to sculpt the outer darkness long after the sun has changed. From our perspective, Neptune's motion feels abstract. The planet lies too far to influence our nights directly, too dim to notice without aid. Yet its presence anchors the boundary of the known system, defining the line between the familiar and the distant. Its orbit resonates faintly with that of Pluto, a 3.2 pattern that keeps the two bodies from ever colliding despite their overlapping paths. That resonance, like so many others in the solar system, owes its existence to steady rotation, the quiet synchronization of spins and orbits across unimaginable distances. Neptune's whirl, though unseen, helps hold the architecture of the outer solar system in harmony. The beauty of Neptune's rotation lies in how unyielding it is. The planet is buffeted by solar wind, struck occasionally by comets, tugged by moons, yet its spin remains unchanged. There's a quiet inevitability to it, as if the planet has found the one rhythm that cannot be broken by external forces. Its day and night come and go with unerring precision, even though the sun's light reaches it weekly and takes over 4 hours to arrive. In the dimness, Neptune's rotation becomes the defining measure of time. If you could stand somewhere nearby, perhaps on Triton's frozen plains, and watch Neptune turn, you'd see an enormous disk of shifting blue clouds rotating against the backdrop of black space. The sunlight, faint and cold, would trace slow gradients across the atmosphere. You'd see white storm systems drift across the equator, casting soft shadows as they moved. Every 16 hours the same patterns would reappear, changed slightly but recognizable. You might begin to sense the planet's rhythm, not as something measured in hours, but as a steady pulse of existence, a mechanical grace that feels more like breathing than spinning. From this distance, the sun's warmth means little, yet the rules remain the same. Gravity holds, rotation persists, and energy moves through cycles that repeat endlessly. Neptune demonstrates that even in near darkness, motion continues with elegance. It doesn't fade, it simply becomes subtle. The planet's steady whirl is a quiet affirmation that the universe doesn't require brightness to sustain rhythm. The dance goes on, even where light barely reaches. As Neptune completes its 165-year orbit around the Sun, its slow journey through space mirrors the patience of its spin. The outermost planet doesn't hurry, It doesn't change course or tilt drastically. It just keeps turning, keeping time for a system that rarely notices. Its rotation links the inner worlds to the outer cold, maintaining continuity across billions of kilometers. In its persistence, it reminds us that motion is not the opposite of stillness, but its foundation. Everything steady is born from movement maintained over time. The winds may howl, the storms may come and go, but the planet itself endures, spinning on an axis set long before life began on Earth. Every rotation carries with it echoes of that first swirling disk of gas and dust, the same momentum that gave rise to all orbits, all tilts, all days and nights. Neptune's steady whirl is not just its own story, it's the solar system's closing note, the last visible verse in the long symphony of motion that began billions of years ago and still plays without pause. Yet even beyond Neptune, the same laws continue. The Kuiper belt stretches outward, filled with icy remnants that also spin and orbit, faint reflections of the same rhythm. Some of them, like Pluto and Eris, are large enough to carry their own moons, their own rotations and tilts. In them, the legacy of Neptune's stability continues. The steady whirl passed from planet to dwarf planet, from world to fragment, from now to eternity. And as the outermost giant turns, its deep blue face illuminated by a sun too far to warm it, it stands as a monument to endurance. The planet spins not because it must, but because it always has. Because motion, once begun, rarely ends. It's a kind of faith written in physics, that energy once set in motion carries on, that cycles continue even when no one watches. Neptune's steady whirl is that faith made visible, a world too distant for detail yet perfect in its persistence, turning quietly in the cold, holding the edge of the solar system in place. Beyond the grand planets that command attention, the giants with their storms, the rocky worlds with their familiar seasons, there are countless smaller companions that orbit quietly in the background. They are the moons, the captured fragments, the remnants of formation. They are the witnesses to every collision, every gravitational tug, every moment of creation that shaped the solar system's history. Some are spheres, round and complete, holding their own delicate balance between day and night. Others are irregular, scarred, barely held together by gravity, yet all of them move with precision. They spin, they tilt, they orbit, they remember. These smaller worlds are easy to overlook because they don't shine by their own light, and they rarely appear dramatic from a distance. But together they tell the continuation of the story the planets began, the story of motion preserved at every scale. For every massive planet that spins, there are dozens of moons turning alongside it, each one obeying the same laws, each one carrying a record of ancient impacts and subtle, gravitational exchanges. The solar system is not a collection of isolated spheres. It's a network of motions, large and small, locked in a shared rhythm that has endured for billions of years. Take our own moon. It is the companion most familiar to us, yet even it is often underestimated. Its orbit and rotation are perfectly synchronized, a phenomenon known as tidal locking. It spins once on its axis in exactly the same time it takes to orbit Earth, so that the same face always looks toward us. That balance is no coincidence. It's the end state of the long-term gravitational friction. When the moon was young, it spun more quickly. Over time, Earth's gravity raised tides on it, not tides of water, but of rock. Those bulges constantly pulled back and forth created heat and gradually slowed the moon's rotation until it matched its orbital period. The process transferred angular momentum from Earth to the moon, slowing Earth's spin slightly and pushing the moon farther away. Even now the moon drifts outward at a rate of about 4 centimeters per year, carrying the memory of that ancient exchange in its motion. The moon's presence stabilizes Earth's tilt, keeping the seasons steady and the climate predictable. Without it, our planet's axis might wander chaotically. tipping from side to side over millions of years. That gentle lunar tug is one of the reasons life has thrived here. It's a quiet kind of partnership, gravity shaping time and balance without sound or intention. Every evening when the moon rises, it's easy to forget that we're watching an ongoing act of motion, a continuation of a story that began in the violence of a collision and settled into grace. The other planets have their own companions, each with its own relationship to rotation and orbit. Mars has two small moons, Phobos and Deimos, irregular rocks that likely began as asteroids, captured long ago by the planet's gravity. Phobos orbits so close to Mars that it circles the planet faster than Mars rotates, rising in the west and setting in the east several times a day. Its orbit is slowly decaying, and in tens of millions of years it may break apart, forming a temporary ring around Mars before falling inward as debris. Deimos, farther out, moves more gently, stable and detached. The two moons represent extremes of motion, one hurrying toward destruction, the other gliding in quiet perpetuity. Both are reminders that gravity never truly releases what it captures. It only reshapes the terms of the relationship over time. Jupiter's moons form a system so vast it could almost be a miniature solar system of its own. There are at least 95 known moons orbiting the giant, and more are still being discovered. The four largest, Io, Europa, Ganymede and Callisto, have been observed for centuries. They orbit in perfect rhythm, locked in gravitational resonances that keep their motion stable. For every orbit of Ganymede, Europa completes 2, and Io completes 4. This resonance generates tides within the moons themselves, flexing their interiors and creating heat. On Io, that heat drives constant volcanic eruptions, the most intense in the solar system. On Europa, it keeps an ocean liquid beneath an icy crust, possibly providing a home for life. On Ganymede, it sustains a magnetic field, rare among moons. Every one of these features, volcanoes, oceans, magnetism, exists because of motion, because of orbits and spins locked in delicate, ceaseless interplay. Saturn's moons add another layer of complexity. Some are large and nearly spherical like Titan, while others are tiny and irregular, no bigger than mountains. Titan is particularly remarkable. It is the only moon with a thick atmosphere, rich in nitrogen and methane, and it experiences weather cycles of rain and evaporation, not of water, but of hydrocarbons. Its rotation is locked to Saturn's orbit, just like our moons to Earth, so one hemisphere always faces the giant planet. As Titan moves, the sun traces long arcs through its sky, filtered through orange haze. Lakes glisten near the poles, and winds sculpt dunes across its surface. Every one of those features owes its existence to Saturn's gravity and rotation. The same spin that keeps the rings aligned also governs the tides in Titan's seas, proving that even at these distances movement holds everything together. Many of Saturn's smaller moons play direct roles in maintaining its rings. Some orbit within gaps, acting as shepherds that keep ring particles confined to narrow bands. Others share orbits, trailing or leading one another in stable patterns. These arrangements seem intricate, but they follow simple physical principles. When two bodies orbit a larger one, their mutual gravity can create resonances that maintain equilibrium. The result is a system that looks fragile but is mathematically robust, a choreography of countless small worlds, each influencing the others with imperceptible precision. Farther out, Uranus and Neptune have their own families of moons, most of them discovered only recently. Uranus's largest moons, Titania, Oberon, Ariel, Umbriel, and Miranda, orbit along the planet's tilted equator, which itself lies nearly sideways relative to the Sun. That means each moon experiences the same long seasons of light and darkness as the planet. For decades, their poles are bathed in sunlight. For decades, they sleep in shadow. The strange orientations of their surfaces, canyons, fractures, and ridges, hint at ancient heating events, likely caused by tidal interactions when the moon's orbit shifted after impacts. Even here, in the faint light of the outer solar system, motion leaves its trace in stone. Neptune's largest moon, Triton, orbits backward against the direction of the planet's spin. Its path is steeply inclined, a relic of the moment it was captured from the Kuiper belt. This retrograde motion means that tidal forces are slowly pulling Triton inward. Over billions of years, it will likely be destroyed, its remains forming rings around Neptune. For now, it's one of the most geologically active bodies in the solar system, with geysers venting nitrogen gas into space and a surface continually renewed by frost and sublimation. Its backward orbit doesn't defy physics, it demonstrates it. Every movement is an expression of conservation, momentum balanced across collisions, capture, and time. Beyond Neptune lies another region filled with small forgotten worlds. The Kuiper belt stretches outward like a vast frozen archive of the early solar system. It contains thousands of objects, some small, some large enough to be considered dwarf planets. Pluto, Eris, Haumea, and Makemake are the best known, but there are countless others, each with its own orbit and spin. Many have moons, even double systems where the moon is nearly as large as the planet itself. Pluto and Charon, for example, are locked together in a dance where both bodies show the same face to each other, orbiting a shared centre of mass in empty space. Their mutual rotation is perfectly synchronised, an eternal pairing formed from balance and inertia. The dwarf planets often have extreme tilts, elongated orbits, and slow spins, reflecting the chaos of their formation. Pluto's day lasts a little over 6 Earth days, its axis tilted by more than 100 degrees. Seasons there unfold over centuries, and sunlight falls at strange angles across mountains of ice and plains of frozen nitrogen. Every rotation, every orbit, is a reminder of the collisions and gravitational tugs that shaped them. They may seem insignificant compared to the major planets, but they preserve conditions that no larger body could, untouched, unchanged, holding memory in their orbits. Further still, in the scattered disk and the hypothetical Oort cloud, trillions of icy objects drift, their spins and tilts unknown. Some are dormant comets, waiting to be nudged inward by distant perturbations. When they do, they light up as they approach the sun, tails of vapour and dust marking their paths. Each one spins as it travels, sometimes tumbling irregularly, sometimes locked into slow, graceful rotation. The diversity of those motions mirrors the diversity of the early solar system itself. They are fragments, but they move with the same dignity as the largest planets, governed by the same invisible equations. The forgotten moons and minor worlds are more than leftovers. They are the scaffolding of the solar system, the connecting tissue between the grand bodies. Their motions influence the stability of everything else. Resonances among small objects help maintain planetary orbits, distribute debris, and regulate the balance of angular momentum across the entire system. When we map their trajectories, we find patterns everywhere, ratios of motion, synchronized periods, and alignments that repeat over vast timescales. Even chaos has structure when observed from a wide enough view. In the quiet of deep space, these small bodies continue their rotations undisturbed. They don't make noise, they don't shimmer brightly, but their constancy is profound. Each turn, each orbit, each wobble contributes to the overall balance of the solar system. They are the background rhythm that allows the larger symphony to play in harmony. And just like the planets, their spins were set long ago during the violent youth of the system. Impacts, collisions, and gravitational exchanges imparted momentum that has persisted for billions of years. Every small world carries a record of that beginning, an unspoken memory of the first moment when dust began to move, when matter became motion. The diversity among them is staggering. Some rotate in hours, others in days. Some tilt gently, others tumble unpredictably. Some are spherical, their gravity strong enough to mould them into symmetry. Others are irregular, shaped by chance. There are binary systems where two bodies orbit each other so closely that they appear as one, and distant companions barely held by gravity, circling each other in slow, cautious motion. There are contact binaries, objects that drifted together until they gently fused, forever locked in shared rotation. Every configuration, every shape is a natural consequence of time and energy. If you could drift among them, the silence would be complete. You would see faint light from the sun glint off icy surfaces, revealing subtle rotations. A small world might spin slowly, casting alternating patches of brightness and shadow. Another might tumble, its motion irregular, unpredictable, but not random. Farther away, faint points of light would trace arcs across the stars, each one another moon or dwarf planet turning on its own axis. None of them would seem aware of the others, yet all would move together, participants in the same cosmic choreography. Over time, even these forgotten worlds change. Impacts still occur, though rarely. The slow pull of planets alters their orbits. The distant tug of passing stars disturbs the Oort cloud, sending new comets inward. Each event rebalances motion ever so slightly. The overall pattern remains, but the details evolve. It's a reminder that nothing in the solar system is truly still, not even the coldest, most isolated fragment. Everything turns, everything drifts, everything remembers. The moons and minor worlds also remind us of scale. That importance in the universe isn't measured by size or brightness, but by participation. Each small body contributes gravitationally to the stability of the system, no matter how faint or distant. The solar system isn't a hierarchy, it's a collaboration of motion. The forgotten moons and minor planets are proof that every piece, no matter how small, has a role in the balance of the whole. Their existence also challenges our sense of what a world is. Once planets were defined by simplicity, things that orbited the sun and shone steadily in the sky. But as we discovered these smaller worlds, that boundary blurred. They may not dominate their orbits, but they embody the same principles. They spin, they tilt, they hold moons of their own, they shape space around them. The line between planet and fragment is more philosophical than physical. Every one of them is a world, simply on a different scale of motion. In the distant cold, where sunlight fades into starlight, these small bodies keep the memory of the beginning alive. They are fossils of the disk that once swirled around the newborn sun, remnants that escaped incorporation into larger planets. Their orbits may be eccentric, their paths tilted, but they persist. They orbit faithfully, completing revolutions that take centuries or millennia, indifferent to the passage of time as we understand it. To them, motion is time, an endless loop that neither begins nor ends, only continues. And so, while the great planets capture attention with their size and power, it is these smaller, quieter bodies that complete the story. They are the punctuation in the language of motion, the details that give it depth. The forgotten moons, the minor worlds, the drifting comets. They fill the spaces between the familiar and the unknown, ensuring that the solar system is not an empty void but a continuum of movement. Every one of them spins in silence, bearing witness to the same forces that shape everything else. From the smallest rock tumbling in the Kuiper Belt to the largest moon orbiting Jupiter, all follow the same pattern, a steady, unending act of turning. It's a truth so simple it almost disappears into background thought, yet it holds the entire cosmos together. Every rotation maintains balance, every orbit sustains harmony. The forgotten moons and minor worlds may seem insignificant, but without them, the music of motion would be incomplete. They are the quiet notes at the edge of the solar symphony, faint, persistent, and absolutely essential. When we look at planets and moons, we often think of them as fixed spheres, solid and complete, turning predictably through space. Yet what defines the difference between a frozen wasteland and a world teeming with life is often something as subtle as a lean. The tilt of a planet, its inclination relative to its orbit, can determine whether oceans freeze or flow, whether air circulates gently or collapses into stillness, whether climates remain stable enough for life to persist. Tilt is not a mere geometric feature, it is a sculptor. It shapes the atmosphere, the weather, the balance between warmth and cold, and even the rhythm of life itself. It is the invisible hand that carves habitability out of motion. On Earth, this hand is gentle. Our axis leans at about 23.5 degrees, and that modest inclination gives us seasons. It ensures that sunlight migrates across latitudes through the year, warming and cooling different regions in turn. Without it, the equator would bask perpetually under the sun while the poles remained locked in eternal cold. The world would split into bands of climate, unchanging and rigid. With the tilt, the boundaries shift, the air moves, and the cycle of life unfolds in response. Plants bloom and wither, animals migrate, water circulates through rainfall and snow, and humans build their calendars around light's slow journey north and south. But the same principle that makes Earth dynamic can also lead to instability elsewhere. Mars, for instance, has no large moon to hold its axis steady. Over millions of years, its tilt swings wildly, sometimes reaching as high as 60 degrees. When that happens, sunlight floods its poles, melting ice and releasing carbon dioxide into the atmosphere. The resulting greenhouse effect warms the planet, possibly enough for water to flow. Then, as the tilt swings back, the poles freeze again, the air thins, and the world returns to cold silence. For any life that might have existed there, these shifts would have been catastrophic. Tilt can make a planet breathe, but it can also make it gasp. Venus, on the other hand, barely tilts at all, just 3 degrees. Its seasons are non-existent. The entire planet bathes in near-constant sunlight, distributed evenly by its thick atmosphere. Without seasonal contrast, there is no exchange of heat between poles and equator, no dynamic weather patterns to moderate temperature. The result is stasis, a world locked in a runaway greenhouse, where uniform heat becomes oppression. The near-zero tilt, coupled with the slow retrograde spin, erase the planet's capacity for variation. It's a demonstration that balance in the cosmos does not mean sameness. It means movement between extremes. At the other end of the scale lies Uranus, whose 98-degree tilt has turned it sideways, leaving one hemisphere in sunlight for decades and the other in shadow. In that configuration, habitability becomes nearly impossible. Energy is distributed unevenly for most of its orbit. The planet's atmosphere adjusts slowly, but never enough to equalize the poles. It's not a matter of temperature alone. Such an orientation disrupts the circulation of gases, the chemistry of the upper atmosphere, and the stability of the planet's climate. For life as we understand it, even simple microbial life, that imbalance creates conditions too extreme to sustain over geological time. Tilt there becomes a sculptor of contrast rather than continuity. The relationship between tilt and habitability extends beyond the solar system. As astronomers observe exoplanets orbiting distant stars, one of the most critical unknowns they seek to understand is axial tilt. Temperature and atmospheric composition matter, but tilt determines how those elements interact over time. A planet with a slight inclination can distribute heat gently, preventing extremes. A planet with too much tilt may experience rapid and destructive climate cycles. The sweet spot, enough inclination to create seasons, but not so much that the poles swing violently, is rare. In that small window, a planet can maintain the kind of long-term stability that allows complex ecosystems to evolve. What makes tilt such a powerful sculptor of habitability is its influence on energy flow. The sun delivers power unevenly, concentrated near the equator and diffused near the poles. The tilt changes how that energy is distributed through the year. It determines where storms form, where ice accumulates, and how oceans and air circulate. On Earth, the tilt drives Hadley cells, the great conveyor belts of air that transport heat from equator to mid-latitudes. It shapes jet streams, monsoons, and the rhythm of ocean currents. These patterns moderate temperature, keeping the planet from tipping too far toward heat or cold. In the absence of tilt, those systems would weaken and equilibrium would break. Life thrives in environments that fluctuate gently, not static, but not chaotic. The tilt provides that modulation. It introduces variability within limits, giving ecosystems time to adapt. The slow drift of sunlight north and south each year teaches organisms to respond. Trees sense changes in daylight length and prepare for winter. Animals time migration and reproduction to match the movement of warmth. Even microbes in the ocean respond to seasonal changes in light and nutrient flow. The tilt, in this sense, is part of the planet's biological clock. It doesn't just shape geography, it shapes behaviour and evolution. Yet tilt also interacts with deeper processes, linking a planet's interior to its surface. The presence of a large moon, for example, can stabilise tilt as it does for Earth. Without the moon, gravitational interactions with other planets might have caused Earth's axis to wobble chaotically, triggering rapid and unpredictable climate shifts. That stability has allowed life to evolve in continuity rather than crisis. It's possible that many habitable worlds require such a companion, a moon or massive satellite that anchors the planet's lean. Without it, the sculptor's hand becomes unsteady. Tilt also influences the carbon cycle, one of the key regulators of climate. On Earth, weathering rates depend partly on temperature and rainfall, both of which vary with the seasons. When the tilt increases slightly, warmer summers enhance weathering, drawing down carbon dioxide and cooling the planet. When the tilt decreases, cooler summers slow the process, allowing greenhouse gases to build up and warm the world again. Over millions of years, this feedback stabilizes global temperature. The result is not perfection, but resilience, a system capable of absorbing fluctuation without collapse. If you imagine a planet without tilt, you imagine a static climate, perhaps stable for a time, but fragile. Without seasonal mixing, polar ice might grow unchecked, reflecting more sunlight and cooling the planet further. Or heat might build endlessly at the equator, driving evaporation until the air becomes saturated and stagnant. Tilt prevents such stagnation by ensuring that energy moves. It's not simply an axis of rotation, it's an axis of renewal. Even subtle differences in tilt can lead to vastly different outcomes. Consider two hypothetical planets of similar size and composition orbiting the same star. One leans slightly more than Earth, the other slightly less. The first would experience stronger seasons, harsher winters, hotter summers. Ice might melt more completely each year, keeping oceans active and climates dynamic. The second, with weaker seasons, might develop thicker polar ice caps that grow over time, eventually reflecting enough sunlight to plunge the planet into a global freeze. The difference between abundance and desolation could be only a few degrees of inclination. That sensitivity to tilt extends beyond climate into geology and chemistry. Seasonal temperature swings influence how minerals form and dissolve, how gases exchange between ocean and atmosphere, and how ice traps or releases carbon compounds. Over geological timescales, those cycles sculpt the surface itself. Valleys carved by glacial advances, deltas built by seasonal floods, deserts that shift with the movement of rain belts, all owe their existence to tilt. It is not just a sculptor of climate, but of landscape. In studying exoplanets, scientists often search for the habitable zone, the region around a star where temperatures might allow liquid water to exist. But that concept is incomplete without understanding tilt. A planet in the right zone but with no inclination might become stagnant. Another slightly outside that zone but with a strong axial lean might redistribute heat enough to remain temperate. Habitability is not defined by distance alone, but by dynamics. Tilt transforms static energy into living variability, allowing water to move, air to circulate, and ecosystems to find rhythm. The sculptor's influence extends even into time. Over millennia, A planet's tilt can shift due to gravitational interactions, a process known as obliquity variation. On Earth, these changes are subtle, oscillating between 22 and 24.5 degrees. But those small variations, combined with orbital cycles, drive ice ages and interglacial periods. They dictate when glaciers grow and retreat, when deserts expand and contract. Every layer of sediment and every core of ice contains a record of these cycles, marking the heartbeat of the planet's climate. Life adapts to them, not by resisting change, but by evolving alongside it. The artistry of tilt lies in this balance between chaos and order. Too much lean, and the climate swings violently. Too little, and it stagnates. Somewhere in between lies the narrow range where change becomes stability, where life can emerge, persist, and evolve. Earth occupies that range, not by design, but by outcome. It's the result of billions of years of interaction between gravity, rotation, and chance. The sculptor's touch is both gentle and absolute, its chisel carved by physics rather than intention. Other worlds show us what happens when that balance shifts. On Titan, Saturn's moon, the small axial tilt combines with Saturn's own seasons to produce periodic changes in methane rain. Lakes fill and evaporate in rhythm with orbital motion, creating landscapes eerily similar to Earth's, but carved in different materials. On Mars, variations in tilt over millions of years have left layered deposits at the poles, frozen records of ancient climates. On Pluto, the tilt of more than 100 degrees creates long uneven seasons, alternating between frozen and active states as sunlight melts and refreezes nitrogen ice. In each case, tilt determines how a world breathes, how it stores and releases energy, how it expresses time. Even in the smallest bodies, the principle holds. The tilt of an asteroid can influence how sunlight heats its surface, causing a subtle but measurable drift in orbit over centuries known as the Yarkovsky effect. Tiny as it is, that effect can change trajectories, leading to collisions or captures. The same physics that governs planetary habitability also governs the movement of the smallest stones in space. Tilt is universal in its reach. When we look back at Earth with this understanding, it becomes clear that our world's habitability is not a static gift, but a dynamic equilibrium. The tilt has changed slightly over time, but the moon's stabilizing pull has kept it within safe bounds. That steadiness has allowed complex life to flourish, weathering ice ages and warm periods alike. The sculptor doesn't stop working, it merely refines the form, ensuring continuity through adjustment. Every sunrise at a new angle, every shift in the line of sunlight across the globe is part of that ongoing creation. If the axis were to shift dramatically, the results would be profound. Continents would experience new climates, ice caps would migrate, ecosystems would collapse and reform, but even then life would likely endure, adapting as it always has. Tilt doesn't dictate existence, it frames it. It sets the tempo for evolution, the boundaries for change. It reminds us that habitability is not a state to be achieved, but a condition to be maintained through motion. In a way, tilt is a planet's personality, the characteristic that determines how it experiences its star. Some worlds face their suns directly, some glance at them from the side, some roll over as they orbit. Each perspective produces a different story of light and temperature, of change and stillness. Habitability is not about perfection. It's about harmony between these motions. A planet doesn't need to be calm to support life. It needs to oscillate within limits, to vary enough to encourage complexity without collapsing into extremes. If you were to watch Earth from far away, you would see that lean immediately, the tilt that gives rise to the dance of light between hemispheres. You would see the poles glimmer white, then fade as seasons change, the equator shimmering in constant sunlight, the continents shifting hues with the migration of warmth. You would see a planet sculpted not by chance, but by motion made stable. The tilt is not an accident. It's a record of ancient events, the collision that formed the moon, the pull of other planets, the balance of rotation and gravity. From those forces emerged a lean or a just right for life to thrive. Tilt is the sculptor that never sleeps. It doesn't carve in moments, but in millennia. Its tools are gravity and time. It shapes worlds not into forms we can see immediately, but into climates, into cycles, into the continuity that makes existence possible. It's the reason Earth remains blue and green instead of frozen white or barren red. It's the quiet, steady artist behind every season, every migration, every breath of wind. And though it works without awareness, its creations are the closest thing to balance that the universe allows. Motion turned into stability, geometry turned into life. If motion is what gives the universe structure, then stillness is what gives it meaning. Every planet spins, every star turns, every atom vibrates, but beneath that motion there is always something quieter, a background calm, a kind of equilibrium that persists even as everything moves. In the same way that music depends on pauses between notes, motion depends on moments of stillness to make sense. The solar system may seem like a great dance of perpetual motion, but when you look closer, when you let time slow down enough to notice, you begin to see that the entire performance rests upon something deeper, the balance between movement and rest. The planets all spin because of the momentum left from their birth. They keep turning because nothing in space stops them. There is no friction, no air to resist them, no surface to slow them down. Yet, when seen from the vastness of space, they look still. From billions of kilometers away, Earth's rotation is invisible, Jupiter's storms are silent, and Neptune's winds are just faint blurs in darkness. The further you step back, the more motion becomes serenity. Scale transforms turbulence into grace. This is one of the quiet paradoxes of the cosmos, that speed can create calm, that activity can produce stability. The faster a gyroscope spins, the steadier it stands. The same is true of the planets. Their rapid rotations, their orbits at tens of kilometers per second, generate the balance that keeps them aligned. It's not an accident that the solar system feels peaceful when seen as a whole. That peace is the product of motion in harmony. The stillness isn't the absence of movement. It's the state where motion has found its balance. If you were to drift between the planets, far from the gravitational hold of any single world, you would encounter this stillness directly. Out there, between orbits, space seems empty. The sun glows distantly, the stars are fixed points, and time feels stretched. Yet even here, nothing truly stops. Photons stream endlessly outward, particles drift, the very fabric of space expands. But in the silence and cold, those emotions become imperceptible. They merge into background continuity. The stillness of space is not static. It's simply beyond the scale of our perception. On Earth, stillness is relative. We think of it as the absence of sound or motion, but in reality the planet is rotating at over 1,600 kilometers per hour at the equator, orbiting the Sun at 30 kilometers per second, and carried around the galaxy at hundreds of kilometers per second more. Even as we sleep, we're moving through space faster than any sound could travel. Yet we feel no motion at all. We sit still because everything around us moves the same way. Stillness, then, isn't about not moving. It's about moving together. It's about being in sync with your surroundings so perfectly that the motion disappears. The solar system itself is a masterclass in this kind of harmony. Each orbit is a balance between gravity and inertia. The planets fall toward the Sun endlessly but never reach it, their forward motion matching the pull of gravity exactly. This equilibrium is what allows the illusion of stillness to exist. The same principle governs moons around planets, rings around giants, and even electrons around atomic nuclei. The universe sustains stillness not by stopping motion, but by balancing it so finely that it becomes invisible. When you think of tilt and spin, you imagine dynamism, the turning of worlds, the changing of seasons, the restless nature of time. But beyond all that, there is an even quieter rhythm. It's the rhythm of conservation, of energy neither created nor destroyed, only transformed. When a planet finds its perfect rotation, it doesn't tire, it doesn't wear out. It continues, effortlessly, indefinitely, its spin carrying the same energy it has always had, only rearranged. That's what stillness looks like on a cosmic scale. Persistence without struggle. The ancient philosophers used to imagine the heavens as a realm of perfect motion, spheres turning forever in unchanging patterns. They were wrong about the details, but right about the principle. There is a kind of serenity in perpetual motion that resists decay. The planets do not drift aimlessly. They orbit in paths that have lasted for billions of years. Their stillness lies in their predictability. They move, but they do not wander. They spin, but they do not stumble. The stability we see from afar is a product of motion refined through time until it becomes indistinguishable from rest. Even in the most violent systems, in stars collapsing, in galaxies colliding, there is still a core of balance. Forces oppose and complete each other, creating temporary chaos that always settles into new order. Motion seeks symmetry. It always has. A collapsing star rotates faster to conserve angular momentum. A spiral galaxy maintains its form through rotation. Every form of turbulence eventually becomes pattern. It's as if the universe refuses to let movement be random for long. Out of motion, it sculpts form. Out of chaos, it sculpts stillness. This pattern extends beyond physics into perception itself. Our eyes and minds are drawn to motion, yet what we find most beautiful is often stillness. A sunset frozen in time, the calm of the sea between waves, the steady glow of a planet in the night sky. What we're responding to is balance, the point at which motion and rest become one. Earth's rotation creates day and night, but sunrise and sunset give us the illusion of pause. The same is true on every world. There are moments, however brief, when a spinning planet aligns perfectly with its star, when light balances with darkness, and stillness briefly becomes visible. In the long perspective, even rotation itself slows. Tides, friction, and energy transfer gradually drain momentum. Earth's day lengthens by fractions of a second each century. The moon moves farther away. Over immense spans of time, every system loses a little of its spin, trading motion for heat, rotation for rest. But even this process follows order. The slowing is even, measured, predictable. The stillness it approaches is not abrupt. It's gradual, like a pendulum easing to its center. The universe doesn't rush toward silence. It glides. This transition from motion to stillness is not decay. It's evolution. When rotation slows, new balances form. Moons synchronize with planets. Planets align with orbits, and eventually systems settle into states of equilibrium. That's what happens when the energy of motion has nowhere left to go. It becomes structure. It becomes geometry, alignment, synchronization. Stillness is not the end of motion, but its final, perfected form. In the outer solar system, where Neptune and its moons drift in quiet darkness, this balance is almost complete. The orbits there change so slowly that to human senses they might as well be frozen. The sunlight that reaches them is faint but constant, enough to sustain cycles that repeat endlessly. Time, there is a soft current, not a tide. The planets still rotate, but their rotation feels detached from urgency, a gesture of continuity rather than of necessity. That's what stillness beyond motion looks like. Persistence without resistance. If you could observe the entire solar system from above, you would see this stillness clearly. The planets move in their orbits, yes, but in patterns that never collide, never break rhythm. Each path is a continuation of the others. The inner worlds move quickly, the the outer ones slowly, but together they form a single choreography. The sun, at the centre, rotates too, its own spin dictating the behaviour of magnetic fields and solar winds. Yet the whole system appears serene, like a mobile hanging in air, each piece turning quietly in the light. From that vantage, the sense of motion disappears entirely. All that remains is balance, an eternal tableau of movement so perfect it has become peace. Even light itself embodies this paradox. It is the fastest thing in existence, yet to the photon there is no passage of time. From its own perspective, the journey from sun to earth takes no time at all. Infinite speed produces perfect stillness. The laws of physics merge motion and rest into the same truth when seen from different perspectives. The stillness beyond motion isn't just a poetic idea. It's built into the structure of the universe. Our own experience of stillness is shaped by this same relationship. When we sit quietly and feel at rest, it's not because the world has stopped. It's because we've aligned ourselves with its motion. The same forces that move planets through space are moving through us. The air we breathe rotates with the Earth. The atoms in our bodies spin and vibrate. The molecules that make up our cells drift with the planet's orbit around the sun. To be still, truly still, is to be in harmony with all that movement, to let it happen without resistance. This understanding reshapes how we think about time. Motion measures time, stillness experiences it. A spinning world marks hours, days, and years. A balanced one feels no urgency. When you look at the night sky and see stars that seem motionless, you're actually seeing their stillness through motion. Light that has travelled for centuries, unbroken, steady. The illusion of calm comes from duration. The longer a motion persists, the more it begins to resemble rest. The same principle applies to the lives of stars. They burn, they expand, they collapse. But even these grand cycles follow rules that bring them to equilibrium. When a star like our sun exhausts its fuel, it doesn't simply die, it transforms. It becomes a white dwarf, a small, dense remnant that spins slowly, radiating its remaining heat for billions of years. Its light fades gradually, approaching stillness asymptotically, never reaching absolute zero. Even death in the universe is a kind of balance. Motion reduced, not erased. The ultimate stillness, if such a thing exists, would not be silence or absence. It would be balance so perfect that no further change could occur. Physicists call it thermodynamic equilibrium, a state where energy is evenly distributed and nothing more can happen. The universe, in its far future, may approach this state. When stars have burned out, planets have cooled, and all motion has slowed into uniform calm. But that scenario is not an ending. It's a transformation. Even in such stillness, particles would drift, fields would exist, and the fabric of space-time would remain. Stillness beyond motion isn't emptiness, it's completeness. You can see glimpses of that completeness even now, in small places, in the still surface of a lake under the morning sun, in the silence of space between planets, in the stable orbit of a moon. These are moments where motion and rest coexist perfectly, where energy flows without turbulence, where time feels suspended. They remind us that the universe doesn't always express power through speed or change. Sometimes it reveals its depth through patience. The stillness beyond motion is what everything moves toward, not as a destination, but as a tendency. Every spin, every orbit, every vibration seeks balance. The planets have already found it. Their motions no longer change significantly. Their spins may slow imperceptibly, but their patterns endure. In that endurance lies the quiet truth, that motion, refined over time, always moves toward peace. If you were to look back at the solar system from the edge of interstellar space, perhaps from the vantage of one of the Voyager probes now drifting beyond the sun's influence, you would see it as a single point of light. All the motion of the planets, all the spins, all the seasons and storms compressed into stillness. From that distance, everything we know becomes one steady glow in the dark. That is what stillness beyond motion truly is. The sum of every movement held together, unified, continuous, calm. The universe has never stopped moving. Even in the quiet moments when everything seems frozen, when stars appear fixed in the blackness and planets glide soundlessly along their paths, everything is still turning. Every atom, every particle, every cloud of gas, every galaxy, all of it is in motion. The illusion of stillness we sometimes see is only a matter of perspective, a trick born of scale and distance. When we look closely enough, there is always a spin, a drift, a rotation somewhere. The cosmos itself is a great wheel, turning without beginning or end. The sun spins slowly at the centre of our solar system, dragging its magnetic fields through space, releasing flares of energy that ripple outward. Around it, the planets trace their steady ellipses, each one balancing gravity and motion in an endless act of equilibrium. Their moons orbit them, the rings shimmer around the giants, and the smaller bodies, asteroids, comets, fragments of ice and stone, follow their own invisible trails, intersecting, colliding, scattering and reforming. All of it together forms a pattern so intricate that it feels alive, yet there is no consciousness guiding it, no hand directing it. It simply continues because motion, once begun, doesn't stop. Even our galaxy spins. The Milky Way rotates like a vast pinwheel, its arms sweeping around the centre once every 200 million years. Every star, including the Sun, follows that rotation, bound by gravity to the galaxy's invisible mass. We are moving even now, carried along at hundreds of kilometers per second, though we feel nothing. There is no wind in this motion, no resistance. Space offers nothing to push against. So the turning continues effortlessly, endlessly, silently. The stillness we feel is not the absence of movement, it's perfect continuity. From this cosmic perspective, the act of rotation becomes something more than mechanics. It becomes a memory. Every spin, every orbit, is the remnant of an earlier motion, a collapse, a collision, a swirling of dust around a newborn star. The planets still turn because of the momentum inherited from their formation. The stars spin because they were born from rotating clouds of gas. The galaxies whirl because the universe itself, from its very beginning, contained asymmetries that caused matter to twist as it expanded. The spin we observe everywhere is not a new thing. It is the preserved imprint of the universe's birth. Each rotation is a signature of that origin. When you consider that everything we know, everything that exists, has been turning since the beginning, a strange comfort emerges. The chaos of creation was not random. It followed laws so precise that they still hold after billions of years. The same laws that set Jupiter spinning, that tilted Earth just enough for life to thrive, that tipped Uranus onto its side, that sent comets looping through the dark, those laws still govern every movement now. Nothing is lost. Energy changes form, but the sum of it remains constant. The universe remembers through motion. That remembrance extends even into the smallest scales. Inside every atom, electrons move in regions of probability, forming clouds that circle nuclei with unimaginable speed. The energy of those motions defines matter itself. The spin of subatomic particles, though abstract and quantum in nature, underlies the structure of all that is. Even the most solid object, even the rock that seems perfectly still, is a storm of motion beneath its surface. Vibrations, rotations, oscillations, all balanced into stability. Motion and matter are not separate things. Matter is what motion looks like when it becomes consistent. At larger scales, galaxies drift toward one another, pulled by gravity through the expanding universe. Clusters of galaxies rotate around common centers, and the cosmic web, the structure of filaments connecting all of it, also twists slowly as it evolves. Even the expansion of the universe, the outward movement of space itself, is a form of turning. Not rotation in a literal sense, but transformation. energy and distance expanding in every direction, the infinite unfolding of motion without opposition. There is no edge where it stops. There is only more space, more movement, more continuation. We often think of turning as circular, but the universe's motion is not confined to loops. Every orbit drifts, every axis precesses, every path changes over time. The circles are spirals slowly unfolding, carrying matter outward. Even on Earth, the rotation of the planet interacts with its orbit to create precession, a slow wobble that traces a cone in space every 26,000 years. The North Star changes, the constellations shift, and the sky reorients itself, though the process is so slow that it feels eternal. Everything, even the most stable motion, evolves. The universe doesn't turn in place, it turns forward. Still, the cycles within it repeat so reliably that they create the illusion of permanence. Day follows night, year follows year, orbit follows orbit. The predictability of these motions gives us a sense of time, but the truth is that time itself is defined by them. Without rotation, there would be no measure, no rhythm. Motion makes time visible. Every sunrise is the consequence of rotation. Every season is the result of tilt. Our entire perception of change depends on the fact that we live on a turning world. That world has been rotating for over 4 billion years, gradually slowing but never stopping. Each day we experience is slightly longer than the one before it, though the difference is too small to feel. The moon, born from a collision, continues to drift away, carrying away a tiny fraction of Earth's angular momentum. One day, billions of years from now, the two will lock fully together, Earth always showing the same face to the moon, just as the moon does to Earth now. Day and month will become the same length. The spin will not vanish. It will simply find new balance. That is how the universe works. Motion doesn't die, it transforms. The same transformation happens everywhere. Jupiter's fast spin drives storms that may last for centuries. Saturn's rotation keeps its ring stable, though they too will change, the particles gradually falling inward, vanishing into the planet over millions of years. Uranus rolls on its side, its long seasons exchanging light and darkness in a rhythm no human could experience directly. Neptune turns in the distant cold, its steady whirl continuing as though unaware of time. The moons spin in sympathy, each locked to its parent world or to resonances with others. The entire solar system, from the Sun to the Kuiper Belt, is one great conversation of motion. It's a harmony so vast and so ancient that it continues whether or not anyone observes it. If you could step outside it all, far beyond the orbit of Neptune, beyond even the farthest comets, and look back, you would see the Sun as a single bright point surrounded by faint moving sparks. Every planet, every moon, every ring and belt would merge into one system of movement, a quiet clockwork suspended in blackness. The scale would make the motion invisible, but it would still be there. Every spin, every orbit, every tilt preserved in silence. From that distance, the solar system would seem motionless, yet its stillness would be the purest form of motion, equilibrium across billions of moving parts. The longer you look, the more you realize that everything we call motion is simply balance expressed through time. Rotation prevents collapse, orbit prevents falling, tilt prevents monotony, even decay, even loss of spin is balance achieved at a slower pace. The laws that govern these things are not temporary, they do not fade, they extend across every scale, from dust to galaxies, from atoms to universes. The cosmos keeps turning because that is its nature. To preserve what was once set in motion, to let energy flow without exhaustion. There is no known reason why it should stop. Entropy increases, yes, but that only redistributes energy. It doesn't remove it. When stars burn out, their remnants still spin. When galaxies age, their cores continue to rotate. Even black holes, the endpoints of stellar collapse, retain angular momentum. Their immense gravity traps everything, even light, yet they themselves turn, dragging the fabric of space-time around them in immense, silent whirlpools. At the far edge of physics, where matter and energy blur, rotation still exists. Motion is not erased even by collapse. It is woven into the geometry of existence itself. From our human perspective, these motions unfold on scales too vast to comprehend. We experience only fragments, a single day, a single orbit, a lifetime measured against cycles that span billions of years, and yet within that narrow window we can sense the continuity. We feel the turning of the earth beneath our feet, the slow drift of shadows, the movement of stars across the night sky. We align our lives to these motions without thinking. Our bodies follow rhythms born of rotation, the sleep-wake cycle, the changing of light, the pulse of days and nights repeating. Even our biology is synchronized with the planet's spin. We are, in every sense, participants in the same motion. This connection between the human and the cosmic is not poetic, it's physical. The atoms in our bodies were forged in stars that once spun and died. The iron in our blood, the calcium in our bones, the oxygen we breathe, all came from the debris of rotating suns that collapsed and exploded. Our very existence depends on spin. Without it, there would be no mixing of elements, no generation of magnetic fields, no planets coalescing from disks of dust. We are made from the residue of motion, from matter that once turned and still carries that rotation within it. The universe spins through us as much as we move through it. When we gaze at the night sky, what we're seeing is not stillness, but history. The light from stars that left them long ago, travelling through expanding space. Each point of light is a place in motion, a sun turning around a galactic centre, a system of planets orbiting unseen. The constellations look fixed, but they're shifting slowly, their shapes changing over millennia. Even the patterns we use to orient ourselves are transient. Everything we look at is changing. It only appears still because we are moving with it. There is comfort in that realization. The permanence we seek has always been an illusion, yet it doesn't make the universe less beautiful. If anything, it makes it more profound. Everything changes, yet everything continues. The turning never stops. The planets rotate, the stars revolve, the galaxies spin, and even when they fade, their motion becomes part of something larger. The universe itself may expand forever, its energy spreading thinner and thinner, but it will still be turning, not in circles we can see, but in the quiet persistence of the laws that began it all. The steady continuation of motion is what makes time possible, but it also dissolves the need to measure it. For the universe, there is no hurry. It doesn't move toward an end. It simply unfolds. The turning we see in planets and stars is only the visible part of a much deeper rotation, one that includes everything. Matter turns into energy, energy into space, space into time, time into memory, and then the cycle begins again. The universe is not a mechanism, it's a continuity, a flowing pattern without rest or origin, only balance. If you were to listen closely enough, not with ears but with awareness, you might sense that rhythm in everything. The orbit of Earth, the pulse of a heartbeat, the pattern of seasons, the rotation of galaxies, all of them are variations of the same universal movement. It is not a sound, but a presence. It is not something that begins or ends. It is something that has always been. The universe is not just still turning. It is turning through us, through every cell, through every breath. There will come a time when the sun changes, when Earth's oceans evaporate and its rocks melt, when the solar system itself grows quiet. But even then, the atoms that once formed these worlds will continue their own motion. They will drift outward, become part of new clouds, new stars, new planets. Somewhere, new worlds will turn, tilted in their own ways, spinning in new light, remembering through motion what came before. The turning will not stop. It will never stop. It is the universe's only constant. And as that motion continues, somewhere, Someone will look up at a night sky under another star on another planet and wonder at the same stillness we do now. They too will be moving without knowing it, carried by the spin of their world, by the orbit of their sun, by the rotation of their galaxy. They too will live in the balance between motion and stillness, and the universe, vast and indifferent, will keep turning, as it always has, as it always will, quietly, steadily, endlessly,